Elaborate templates, latex templates.
You speak about infinite temperature bootstrap. So first we'll wait for just a few minutes, a few seconds, and yes, because powers, but to interpret the other
Go. Okay, thank you very much, Paolo. So good morning, everyone. Today I'm going high tech. This is a technical talk, so it's going to involve slides. I'm going to be talking about this paper, which appeared last August. It has all the ingredients that we discussed yesterday in the morning and the afternoon. It is a work written in collaboration with my long-term outstanding colleague, Vasilis Niarchos, who's at the University of Crete, with my fantastic PhD student who's applying for jobs, postdoc jobs, Mitchell Woolley, and with Alex Ratudakis, who is a very impressive character. I think I've told some of you that he's a master's student who has been working as a commando firefighter throughout his undergrad and postgraduate studies full-time, and contributed very significantly both on the computational sort of coding and formal aspects of this paper. So he's applying for PhDs everywhere in the world. I hope he does very well. He really deserves it. Okay, so let's begin. There's going to be a lot of recap of what we. No, there we go. There's going to be a lot of recap of what we discussed yesterday, which hopefully is not going to be too boring. So what is the bootstrap philosophy? Since I'm going to be talking about the bootstrap, is the idea that if you've got a set of consistency conditions in your theory, it should be enough, at least that's what the philosophy says, to determine the physics completely. There was a hope at some point in the previous century that the S matrix of quantum field theory, that for strong interactions, for example, would be completely determined using the principles of analyticity, unitarity, and crossing. It turned out that this was not the case, but this kind of idea originates from these kinds of hopes. And QCD came along and provided a framework for actually working with strong interactions. But a version of this original idea is used to great effect in what is now the modern conformal bootstrap, which is a thing where kind of bootstrap philosophy was revived and now spread to many different applications. So in my context, I'm interested about CFTs. We discussed CFTs yesterday. They are ubiquitous. They appear in the study of quantum field theory at UV and IR fixed points of RG, in the study of critical phenomena, and also of interest in the context of this workshop to quantum gravity via the ADS-CFT correspondence. But there are many other applications of the conformal, of the bootstrap, I should say, philosophy. There's something known as the modern S-matrix bootstrap, where people are still trying to constrain scattering amplitudes for certain theories. There's something known as the cosmological bootstrap, where people try to constrain cosmological correlators. There's a matrix quantum mechanics bootstrap, a modular bootstrap. So all these ideas of originating from the modern conformal bootstrap have different applications. Okay, so the motivation behind my work and my talk today is that the conformal bootstrap opens up the way for a non-perturbative approach to solving CFTs. And in particular, there are very powerful numerical methods that one can implement that lead to very impressive results. We saw yesterday that you can repackage the crossing equation in a set of sum rules. So here I'm being very, very schematic. The sum rules essentially involve summing over the spectrum of operators characterized by scaling dimensions and spin. This I denote collectively with this the product of, let's say, OB coefficients, for example, in conformal blocks, depending on what kind of problem you are studying. Here I'm making some assumption that there is some kind of discretization of my of the space in which these functions take values, so that I can put this problem in a computer. But in principle, there are infinite unknowns. These sums are unconstrained. And it turns out that traditionally the way that these parameters enter these functions or these vector components lead to non-convex optimization problems. So if I wanted to try and solve this thing directly and say, look, this is the constraint that I have, just solve it. What kind of information do I get about my theory? Doing so directly is hard because performing non-convex optimization is hard. The workaround was the brilliant idea of these people, Ratazzi, Richkoff, Tony, Vicky in 2008, where you can, instead of solving this problem, which goes under the name, as we said yesterday, the primal formulation of the bootstrap, you go to the dual formulation of the bootstrap. And instead of solving this equation directly, you try to scan for the space over the space of linear functionals that maps this problem to a convex linear or semi-definite problem. And there's tools from computer science that people can use to very efficiently scan over the space of linear functionals, getting constraints on CFD data with very good precision. These results, in addition to being high precision, are also rigorous. A bound is a bound. You might improve on that bound, but at least you're sure that what you've obtained cannot be violated. And there are many packages that are now available and easy for people to use. I would say the most famous and popular is the one by Simmons-Duffin from 2015, called SDPB for semi-definite programming B. Okay, so this is what is the, let's say, traditional approach to the numerical bootstrap. However, I would like to revisit the attempt to try and directly solve the crossing equations or the constraint equations arising from a bootstrap setup. And there are various reasons for why one might want to do that. The first one is that there are certain assumptions that go into the setup of the bootstrap problem, and maybe exploring the solution space using this primal formulation is useful towards guiding, feeding into these assumptions for the dual problem and guiding rigorous approaches. Also, these dual formulation in terms of semi-definite programming are very, very hungry in terms of precision. So usually one needs to keep track of hundreds or even thousands of digits of precision. And when you try to scale this, it's very computationally expensive. So maybe we can find some more efficient numerical ways of attacking this problem. And finally, something that I stressed yesterday quite a bit is that applying these linear functional semi-definite programming approaches to the bootstrap relies on having a set of positivity conditions on the coefficients multiplying your conformal blocks. And that is not there in cases where you've got CFDs of finite temperature or CFDs with defects, boundaries. If you want to set up, let's say, the 5-point bootstrap instead of the 4-point bootstrap, non-unitary theories, and so on. So there is a wide zoo of interesting scenarios where this positivity does not apply, and one has to find alternative approaches. Okay, so this is all nice and good, but of course, the primal problem has the issue of involving an infinite number of unknowns. And how do you deal with this infinite number of unknowns? One very, let's say, straightforward and simple way of trying to attack this is to do a hard truncation. So we go back to this sum, and then you say, I just put a cutoff above some conformal dimension, and then hope that my sums converge fast enough so that I approximate the problem in an acceptable way. So this was something that was introduced by Ghiozzi in 2013, some simple theories, and it seemed to kind of work in that case, not obviously reproducing the results that the rigorous bootstrap gives. There's also kind of soft truncation approaches. So we had one in this paper with Vasilis, where we introduced many, many more operators and somehow only kept track of what the CFD data were returning for the very low dimensional operators. And we allowed the other operators to act as soft, let's say, tails of that expansion. You can also use Tarberian theorems, which under some assumptions about the spectrum tell you how, what happens as your conformal dimensions sort of, what the contributions of the high dimension operators actually, how they can be modeled. So all these approaches can be effective for specific cases, but in general, it's hard to control the systematic error. It's hard to kind of say, if it works in one example and you want to transfer it to another example, you don't really know if this approach is going to work. So today, what I will talk about is a new framework for capturing all unknowns using a couple of different tools. One is dispersion relations, and the other one is neural networks. And what that achieves is that we can model the full set of infinite unknowns without dropping any terms in a way that I'm going to make precise. So I will showcase a specific numerical application of this idea. So first I'll introduce this in all generality, and then I will give a numerical application in the context of CFTs at finite temperature, which are dual to black holes in ABS. Okay, any questions up to now? So the main idea is the following. Consider the following split of the sum rule. So this is the sum rule that we had, which again comes, let's say, from the crossing equations, can come at 0 temperature or the analog at finite temperature or any other constraint you may have. And then perform the following split. First of all, we're going to introduce an arbitrary parameter, J star, and then I'm going to call all the operators of any scaling dimension above that have spin above that parameter as the high spin part of my sum rule, of my spectrum. These are going to be approximated by us using dispersion relations, which I will discuss a little later on. Likewise, there's going to be a low spin part where the spin of the corresponding operators, again of any scaling dimension, is going to be called low spin. And then I'm going to further split this into two. There's going to be a low spin, low dimension part. And these are going to be discrete data. So these are going to be sort of in the old way of doing things, just OP coefficients and corresponding sort of log contributions. But then the problematic part, which is the infinite set of operators with dimensions higher than this delta star, are going to be low spin, high dimension contributions, which I'm going to model using a neural network. Okay, so the traditional approach is what we're going to do here. Just discrete data that you can try and optimize over. Then there is low spin, high dimension, which we're going to be approximating using neural nets. And then there is also high spin, which we will approximate using dispersion relations. Okay, so this is the main idea, and I would say the novelty of this approach. I should emphasize that the J star and the delta star are arbitrary parameters. I don't know why this jumped from the subscript to the superscript. It's the same thing. They're arbitrary. In fact, you can choose to move J star or delta star, and that doesn't necessarily make things better, or it makes it better in some ways and worse in some others. So, for example, if I have introduced more discrete data into my problem and lower J star there, I find that, for example, these approximations using dispersion relations are better behaved, but then have more parameters to optimize over. It makes the problem a little more difficult in a slightly different way. Okay, so artificial neural networks. We spoke about artificial neural networks yesterday. I showed you this architecture, the multi-layer perceptron, or MLP. You've got input and output layer and some hidden layers. This is a fully connected neural network. We discussed how each layer takes the contributions from the previous layer, multiplies this with some weight matrix, which tells you how the nodes, for example, for the next layer are populated. Then you can have some shift by some bias vector, and then you hit all this with a so-called activation function. And the parameters of my neural network are these weights and biases, which are learned during training, aiming to minimize a loss. So we discussed all this in some detail yesterday. And the reason why neural networks are useful in our context is that there exists something known as the universal approximation theorem, where for nonlinear activation functions, the neural network at the end, what comes out of as output can approximate a continuous function to arbitrary accuracy. So in our particular application, and I'm jumping ahead here a little bit, this is the low spin, high dimension part that I want to approximate using a neural network. And what am I going to do in this case? Why do functions even arise in the context of what I've described before? Let me go back a couple of slides. We'll see it in a minute, actually. So here, in the case of the finite temperature CFT problem, I have resummed all the contributions corresponding to an infinite set of operators with dimension above my cutoff, delta star. And because of the nature of the thermal block expansion, which again we discussed yesterday, there is a factorization in terms of the dependence of between these theta variables and these r variables. So there's this factorization allows me to approximate the sum over dimensions using a function of one real variable r. So all these things we're going to call the tail functions. There's going to be a tail function for each value of j, which is below j star. And I will approximate all these functions using neural networks. The architecture that seems to work is not a fully connected multi-layer perceptron architecture. It's something known as a multi-branch architecture, where essentially each of these branches is going to provide as output one of these tail functions. So the neural networks we saw are very good function approximators. And in fact, you can use packages where you can now do optimization, both in terms of spaces of functions and also discrete data in one single package. So this is quite an efficient way of putting things together. Great. So the summary so far is the following. First of all, we want to try and find constructive solutions to the sum rules for the bootstrap problem for the reasons that I discussed. I would like to capture the high spin contribution, so I'm splitting in terms of high spin, low dimension, low spin, high dimension. The high spin contributions captured through dispersion relations. I have not discussed this at all yet. And then we optimize, once we've set up this approximation using dispersion relations, you have an optimization problem where you have low spin data contributions in terms of discrete data and neural network functions. The way that we're going to do this, as in any optimization problem, you have to come up with a loss function, a function that you're trying to minimize. It has to be semi-positive definite, so you satisfy it completely if you are able to set this loss function to 0 by picking the values here of the parameters that you're optimizing over. Capital D is the set of my discrete data, low spin, low dimension. Theta is the set of neural network parameters that optimize the low spin, high dimension. A very important part of optimization is choosing the correct loss function. And here we tried a couple of things. The one maybe simplest thing you can do is to choose the LP norm of the crossing vector, so the vector of crossing equations. I'll show you exactly how this is set up. And then another option was to look at a kind of slightly novel dot product loss, as we call it, for the crossing vector. And I'll show you very briefly what these things look like. So the first one is simply the LP norm of your constraint. So for p equals 1, this is just the Euclidean norm of that vector. We chose, for example, to go for p equals 1, and I'll show you how the optimization results differ depending on what choice you make. The other one is a geometric loss that kind of makes use of this, the fact that you can organize, you have these crossing vectors, and it has two pieces. For example, in a case where we have no exposed data and only functions to optimize over, you can set your loss function to have this form. So there's a set of known contributions which you can parameterize in terms of this H vector, like the contribution of the identity or any other input you'd like to put into your problem. And then there are the contributions to the crossing equation coming from these tail functions. And you can choose to do it in two pieces. You can say the first thing I would like to do is to set the angle between these two vectors to be the same, so that these vectors are parallel. And then I would like the magnitude of these two things to be the same. So making the vectors parallel optimizes this piece, sets it to 0. Optimizing this piece to 0 sets them to have the same magnitude. And there is a variation of this if you'd like to have, for example, one exposed datum, a discrete datum that you're keeping track of. In this case, we chose to not introduce this in our loss. We just want these guys to be parallel vectors, and then at the end, if you want this loss to be 0, you get the value of the discrete datum out for free. Get a prediction so that this condition is satisfied. Okay, so this is maybe a little bit technical question.
Okay, can you remind us what are the entries of this curly F?
So the entries of the curly F are the set of crossing equations so the crossing equations usually, I'm talking this here in a bit of generality, but they are usually continuous variables of the two real parameters that appear in your thermal bootstrap, for example, or your zero temperature bootstrap. So they have a continuous dependence on these parameters. In order for you to put it on a computer, you have to have a finite set of constraints.
These are different values of
Very good. So you sample over a lattice, let's say, of points on this cross ratio plane, and each of the components of this vector is. Thank you for the question. Yeah, so this is what these vectors. Other questions? Okay, so let's look at an application in the context of the thermal bootstrap. You should all be experts in the thermal bootstrap now. So again, things that I said yesterday, consider CFT at finite temperature, meaning we put it on a cylinder, RD minus 1 times S1 of radius beta. There is a non-trivial two-point function in that case that depends on two real parameters. You can see that by using symmetries of that problem to reduce the spatial dependence on only one coordinate, and then you have the Euclideanized time. There is a Euclidean KMS condition, which involves your two-point function satisfying this constraint, which is not automatically satisfied. If I perform this parameter, I do this coordinate change to this ZZ bar, it looks very much like what the bootstrap condition for four-point function looks like at zero temperature. Okay, so we would like our thermal CFT data to obey this condition. Now, there is a thermal block expansion for thermal CFTs. We saw a little bit how you can derive this yesterday. It corresponds to taking the OPE of two operators in the thermal vacuum. These are the Gegenbaur polynomials, satisfy some nice orthogonality conditions. And then there is a factorization in terms of the dependence on these two real parameters here, which is nice. These depend only on W e to the I theta, when Z is R e to the I theta in polar parameterization. And then there is an R dependence, which sees the dimension of the exchange operator OPE. These coefficients here are including these thermal one-point functions that we also discussed yesterday. They are defined like so. There is a dependence on the three-point function coefficients of the zero temperature problem, the normalization of the corresponding operator, and this guy also appears there up to some multiplicative factor. And it is important here to notice that because of the structure of this quantity, this does not have to be positive. It can have negative values depending on what values F and B takes. What is the setup of the bootstrap problem on finite temperature? Assuming you know the zero temperature data, so assuming you know what these Fs are, and assuming you know the spectrum of operators, what the deltas are, the KMS condition poses some non-trivial constraints for the thermal one-point functions. But that is for that data. But of course, from the point of view of optimization, and in principle, in practice, we do not know exactly all these data because it's very hard to solve these CFTs at zero temperature completely. This is what the optimization tries to find. And the rest, if you know this data, you can extract explicitly what these thermal one-point function coefficients also. Okay, so now let's get a little bit more specific about how the framework of splitting things in terms of high spin, low spin, and high and low dimension applies to the context of these thermal CFTs. So the first thing that is relatively simple is to just impose these two cutoffs. So a cutoff on the spin and a cutoff on the conformal dimension. And this is the low spin, low dimension part of my expansion for this thermal two-point function. This is identical to what I showed you before. It's just that these deltas take value up to some delta star. Okay, so these are the discrete data because I'm trying to look for a finite set of discrete data during my optimization problem. The second part is the low spin high dimension part, where I have resummed all the operators with dimension higher than delta star because I've got this nice factorization property. So this is going to be some polynomial in some powers, involving some powers of R depending on my dimension. And I'm packaging all this in terms of this function here, which is a function of one real variable. This is what my neural network is going to try and optimize over. So I have some discrete guys, some numbers, and then I have these functions, which are these tail functions. There's one for each j smaller than j star. If I choose j star to have some particular value, I have, let's say, I don't know, j star equals 6. I have a certain number of these things. And depending on whether delta star is high or low enough, I might also have a set of discrete data to optimize over. The last piece to this decomposition is the high spin part. And this can be approximated using what is known as a thermal Lorentz inversion formula. It's a little bit kind of technical to tell you where this thing comes from, but one can essentially rewrite that high spin part as a function of the discontinuity of the continued version of this original 2-point function. So if you sort of continue in W prime, there is some nice analytic structure, there is some cuts for that 2-point function, and you can rewrite the contribution of the higher spin guys in terms of the discontinuity across those cuts. Now you might tell me, hang on a minute, you're trying to find this, but then you kind of, re-expressing it in terms of the same quantity. But it turns out that the contribution that you need to determine the discontinuity is much, there's much less information that goes into that than determining all of this, as we'll see in a minute. Okay. So I should emphasize here that delta star and J star are freely tunable. I can choose, for example, to make this bigger, so I have more terms here, and I have fewer functions there. And then I have to, approximate more terms using this dispersion relation. And we'll see how these things sort of fare as you kind of play a little bit with these values of delta star and J star. But importantly, no terms have been dropped anywhere. And in principle, if I can, approximate these functions really, really well, and I can optimize as well as I can, I have all the information I need about my theory. I have done no truncation. Okay, good. Some more information maybe about this high spin part, which is approximated through these finite dispersion T-dispersion relations. Okay, this is maybe a technical slide, just to show you maybe that this kernel over which I integrate can be determined very, very specifically, some horrible nested thing, but we know this in closed analytic form. And the question is, how well can we, approximate numerically the integrals that appear in the previous slide. Okay, so we also spoke yesterday about generalized free fields. Why? Because we can solve them exactly for thermal CFTs, and we can use them as a nice calibrating case for our approach to see how well what we're doing works or not. So for a generalized free field, which we said yesterday are fields whose correlators factorize without them being necessarily free and having the free conformal dimension, whatever d minus 2 over 2 for scalars. You have an interesting set of composites known as double twist operators, which we discussed yesterday, which are two phi fields sprinkled with boxes and derivatives. The conformal dimension is given by 2 delta phi for 2 phis plus the number of boxes plus the number of derivatives. It turns out that in the OP of phi that I'm interested in for the determination of this 2-point function, I only have even spin contributions. And that's why my spin here is an even number. Okay, and if I want to go to my original thermal block decomposition and just say that the operators that appear in that sum are only these double twist operators, which is what actually is happening, I can rewrite my thermal 2-point function in this way. This is the contribution of the identity, and then this is the thermal 1-point function coefficient times the Gibbon polynomial of these thermal blocks for these scaling dimensions. This is what it looks like. So this is good because I also know an analytic closed form expression for this thermal 2-point function using the method of images. And then I can solve for all these coefficients explicitly. This is a formula that I did not write explicitly on the board yesterday. You can determine all these coefficients based on this exact formula. It's this horrible thing involving these Riemann zeta functions and some other factors. Okay, but I know this problem exactly. So given this knowledge, we can test how good is our approximate KMS condition and the approach that we have been taking. So I'll show you two things here. The first one is a case where I have my delta star low enough, so I have no discrete data. So the only thing that I have is a set of these tail functions. I have also J star to move around, and I can move it from 0 all the way to 8. And here I'm using all the information I have about the analytics of the theory in order to see how well my crossing equation is satisfied. So in fact, my tails are also not going to be optimized. I'm going to use, for example, the first 100 contributions from the double twist operators that I have over there. I know these terms, I can compute them explicitly, I can sum them over. This is what my tail functions should look like. Plug them into my equation and see how well I approximate the high spin part using this dispersion relation. And you see, as I change J star, I start changing J star, I get that the loss, which can be either this L1 norm or this dot loss, kind of decreases. So the more that I go higher in J star, the better I do in terms of loss. And this is relatively good, but this other choice of the loss is much, much, much better as an absolute sort of gauge of how well my optimization is performing. So immediately you see the choice of the loss function makes a difference in, you know, how small you can go in terms of satisfying these constraints. This dot loss seems to be doing very, very, very well, and this is the one that we end up using. If I allow myself to have one discrete datum, one exposed datum, in this case, I'm only showing you the dot loss and changing J star, and you get, again, very, very good values for the loss, very close to 0. And then there is this datum can actually, because of the way we set up this dot loss, can be determined just by plugging in information about your the known parts of your equation. And okay, there's a bit of a technical piece here. What is this datum that I'm keeping track of? Let me show you. It is the coefficient corresponding to having one box and no derivatives, single derivatives, or having two single derivatives and no boxes. And it turns out it's an accident that these things give rise to the same eigenbar polynomial contribution. So the optimizer cannot determine the difference, cannot split the difference between these two coefficients up to some overall factor. So it should have been 0, 2. So the datum that we're tracking is this combination. There is an exact value that one can check. And as you increase J star, you see that this value kind of comes much, much, much closer to the exact result. So what have we achieved with this calibrating step? The approximation that we have using dispersion relations works very well. You can achieve, if you know the analytic solution, very, very low losses and very good exact values. Okay, so this is good. It means that the numerical approximation to this high spin part in terms of dispersion relations works well. So now let's see how well it does if you are agnostic. If you say, I start with my generalized free fields and I try to just solve without inputting any analytic information to compare. So here I'm going to show you a couple of plots. One is 4-dimensional generalized free fields, J star equals 6. We pick a random value of delta phi so that it's not integer or half integer because funny things can happen at these values. In this case, there are 4 tail functions and I have no discrete data to keep track of. And then with the serrated line here, you see the analytic result. And the blue line is what the algorithm returns. So here, because there's a lot of stochasticity in my problem, I can run, there's lots of local minima, which are very close together. So it's not like I run the algorithm millions of times and I get the same answer. Each time I can get something which is slightly different. Some things are better, some things are worse. So the way that we did it is we ran a large ensemble of jobs, about 1,000, and then we kept the top 100 of them in terms of how small the loss could be. The deep blue line is the average of those results, and then this spread that you see here is one standard deviation around that average. So as you can see, this A0 does not do great, this A2 does not do great. There seems to be some flat direction actually in terms of A0 and A2, which we don't quite understand. If you sum them over, however, they seem to be doing a little bit better. A4, A6 seem to be quite good. And what I'm showing you here is just a cross-section on this ZZ bar plane where I'm on the real axis. I can take this thing and plot it on the full cross ratio, thermal cross ratio plane, and it's doing a little bit better, but it's again not that great. So the errors are mostly around, I don't know, the 5% range, which is not great, and then closer to here, they become a little bit worse. So this is okay, but it's not as well as we would like it to be. If I now expose one discrete datum and rerun the process, I have one discrete parameter to also keep track of. This is not an error once again, it's kind of the statistical 1 sigma from the average result that I get from keeping the best runs in this process. And it kind of comes to about 13.3 and the analytic result is 15.2. 0.06. So it's kind of close, but not that close. Here you see, an even worse performance in this particular case. So it's, yes, question?
What is on the y-axis?
On the y-axis is the value of this tail function. So these are the functions that we're approximating using the neural net. Yeah, so you have 1, 2, 3, 4 in this particular case. And on the x-axis is the parameterize the real axis on your cross ratio plane. J star is 6, correct. So so J star is 6, meaning that it's an A0, A2, A4, and A6. So, because they take even spins, yeah. So if I had J star equals 8, I would have one more function. I have more functions to optimize over. My approximation in terms of the dispersion relation actually does better, as I showed you in that plot, but then I have one more function to optimize over. So you increase the number of unknowns, makes the optimization harder. Sometimes. So this. In this case, delta star is just above whatever just above the dimension of this operator, which should be 2 delta phi plus 2. So it's just above that, whatever it needs to be in order to only allow for this operator to be exposed. Mm-hmm. 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 Yes. Sorry, so what's the question? So
AR is to approximate these operators like stuff.
Yeah.
Now I want to do this implementation.
Yeah.
Try something AR.
Yeah. And to extract again, like you could do that.
Then to be consistent, you should be able to find a below that star.
That is true. That is true. We do not try to do that. No. I mean, I guess we're interested in kind of approximating the full function. We did not try to do that. I'm trying to think of how would you do that in practice, right? Because you'd have to kind of assign the deltas, right, where these contributions come in. So then again, you have to make some kind of choice, right? Is another optimization basically where you have some contribution from these functions for each values of this high dimension operator, then you have to split it in terms of thermal blocks for delta 1 and delta 2 and delta 3. Maybe it sounds to me like an extra step that you have to do. And you see, we don't want to do that, right? Because this is initially I could just keep all these guys here and do some cutoff at very high level and ask the optimization to determine all these. But we want to avoid this step. We want to just say, I'm interested usually in the determination of a few either giving the answer for the full thermal 2-point function without splitting it into small bits, in which case I can just give you, I do not keep track of this data and I just give you the tail functions, or I want to keep track of a very small number of these data. Yeah, you say. Yeah, I first of all, I don't know if it would be easy. Maybe there's more than one solution. So I don't know. Maybe you can, yeah, exactly, to say that the thing, if you were to do this decomposition, you get extra constraints by requiring that the operators start with delta star. Yeah.
I'm a bit lost with earlier you showed that your ratios are 15.06 or 49.
Good. Yeah.
And now it's 13.29.
Yeah. So earlier what I did is that these things were the red lines.
Okay.
So this thing with the red lines, and then I get this for free because of the way that I've defined my loss. And if I know the red lines, so here you see I have two things to optimize over: the A0, A2, etc., up to A6, and I have to optimize over the not quite. So here I optimize over this, and I get this value for free as an output. So depending on whether I pick up the red line, which is the analytic result that I know, or I use the blue one, I get a different value. This is what you get with the red. This is what you get with the blue. And so previously I was inputting the answer and seeing how well I can do. Here I'm not inputting the answer. I'm asking the algorithm to find the answer, as if I don't know what the answer is.
And is this because you randomly pick delta phi equal to 1.6?
No, it doesn't. It doesn't depend on the delta phi.
Okay.
Actually,
Okay.
it will be the same. You can choose 1.5. You can choose 1. It doesn't matter. This is a choice again to avoid particularities that take place when delta phi is integer or half integer. Okay. Now, one of the things that we found, however, is that if you provide the algorithm with one additional datum from the analytic solution, let's say 1 point, or let's say where this about the behavior of these functions at 1 point, let's say on this real z-axis, it does a much better job. So if you provide what we call an anchor point, analytic input at r is 0.7, here, for example, this automatically seems to kind of whittle down the space of possible solutions and significantly improves the answer. So you see here the corresponding error that we get at the end is of the order of 1% instead of, whatever, 20, whatever it was in the previous slide. Okay, so you can do this also in the case where you've got one exposed datum. And if you provide one anchor point, it seems to be doing much better. It is kind of up to 2 decimal points, kind of, or 3 decimal points close to the analytic result. So what does that teach us? It teaches us that recovering the approximate correlator, it does not seem to be stable without additional input. And here I'm using this idea of stability in terms of, what happens if I run many times and I provide, for example, the correct or the wrong anchor point. So if I were to provide an incorrect anchor point, I see that I would get like a very big spread in terms of my standard deviation from approximating these functions. But once I provide the correct anchor point, the solution is effectively determined just with 1. So what I'm going to do in the last 15 minutes is try to use this to find a solution to the stability argument. So saying like, how would I know, because this is a stochastic process, about whether what I found is good or not good. It seems to be a reasonable assumption to say that if I find solutions which have a small spread and a very low loss, this is a good guiding principle for me to trust what I'm doing. So what I would like to do here is think about 4D holographic correlators in large N CFTs with the gravity dual. In contrast to what happens for the free field case, I now have a stress energy tensor and a multi-trace or multi-stress tensor contribution, so powers of the stress tensor, and depending on how you contract the various indices, you get things of different spin. There is a corresponding thermal datum, the stress tensor datum. This is for the double twist operators, and this is for the multi-stress tensor components. Note here that you can have situations which have the same spectrum of the theory, but then different values of these thermal 1-point functions. And as we discussed yesterday, this corresponds to different solutions. In fact, we know from the holographic side that you can come up with an arbitrary number of higher derivative gravities, which would correspond to different thermal 1-point functions. Okay, so you expect many solutions. There is a holographic computation that you can do here. You can solve the free wave equation on the black brane background. It turns out that the energy momentum data are completely determined from what happens close to the boundary of ADS. In fact, there is some universality for the lowest twist multi-energy momentum data, where these thermal 1-point function coefficients are powers of the proportional to powers of the stress tensor. So effectively, in your problem, you already know from a very simple ADS calculation the value of this and this. So the thing that you do not know how to compute is this holography, because it requires information about of the solution in all of the bulk. So some questions, for example, for the bootstrap are, can we detect these multiple KMS solutions corresponding to different gravity theories? Can we detect these universality relations that you know from the gravity calculation appear here? And can we recover the double twist data? And what obviously we can do in our calculation, in analogy with what we did for the free fields, is this last bit. Okay, so these are some results for this particular case. We're gonna, again, run this optimizer this time for delta phi is 1.5. I'm choosing this particular value because at the end I will compare with another result from the group of Andrei Parnachev and company from Trinity College Dublin. And we optimize for this particular double twist datum. Here, because we know what the contribution is from the stress tensor sector, we can provide, so one thing that I didn't say is that the dispersion relation approximation of my high spin content relies on the discontinuity. For the generalized free field case, the only term that contributes to discontinuity is the identity, nothing else. So it's very easy to approximate that. When you introduce a stress tensor, there's an infinite set of contributions from multi stress tensors, and there you have to kind of cut it off somewhere. But it turns out experimentally that the higher you go with J star, the better this approximation becomes. And these contributions here you can read off from the gravity result. And you also can provide as input contributions for these thermal one-point function coefficients, again from gravity, which you know explicitly. So to help our approximation, our algorithm even more, what we used is some assumption that the gravity solution is in some sense close to the generalized free field one. So in terms of spectrum, right, it has these additional operators, but it also has this double twist And we decided to start from the analytic solution as a guide, as an anchor point, as we used in the generalized free field case, and then start sort of allowing the algorithm to explore without penalty a region close to the generalized free field solution. And actually what we saw is that as you allowed it to explore, so at the beginning you said like, start with the generalized free field solution, and then if you go away from that, you're just very penalized in terms of your optimization. Obviously, you get something which is very bad. And then you just allow it to explore a larger and larger kind of sphere in this higher dimensional space, where you allow up to some percentage of some size of or some tolerance, I should say, around the generalized free field. And then you see that the loss at the beginning is very bad, then it gets much better, and then it gets bad again. And the optimal value that produces a stable configuration where also your the spreads of your statistical fluctuations is the smallest, is at this value of p equals 0.2. So this contribution to our loss function, where we have the original loss function and we add this kind of tolerance criterion, does exactly the job that I discussed. So we run our algorithm. Again, as before, we run for about 1,000 jobs. We keep the top 100 performing with the lowest losses, and then we average over them, and this is one standard deviation, and we find this number. And this thing can be compared to a recent result. In fact, we coordinated our submissions by Barnachev, Buric, and Gusaev, who used some other techniques which rely on working in the zero spatial separation limit. So as I told you earlier on, we are working with two parameters, tau and whatever x. They work in the limit where x goes to 0. So there you can do actually more, but interestingly enough, you can still try and can constrain this datum, and they have much better access to this data. So instead of just 7 data that we're introducing here in this approximation, they work with about 40. They have some analytic arguments, and they get a number which is relatively close to this, but maybe not as small, 7.6. We get 9.3 plus minus 0.4. So it's relatively close, but not exactly the same. So we're interested in seeing, and I'm going to start concluding, how we can improve this method. I described a new framework for directly attacking the bootstrap without any truncations. We saw that the higher operator dimension tails can be bootstrapped using neural networks. And then I presented some examples in the case of the thermal bootstrap. But the method that I have here can be applied to any other bootstrap context, including where positivity constraints are not available, right? Such as CFTs with defects, higher point bootstrap, and so on. Within this context of finite T, and unlike other approaches, we work at non-zero spatial separation throughout. There's also some papers by Pomoni and collaborators where they use Tauberian theorems to try and do the same kind of thing. They also work at zero spatial separation. And also the work of Barnachev is a zero spatial separation. As far as I know, we are the first to work at non-zero spatial separation. And things to do next, there's many things to do. I mean, I have not particularly optimized the optimization process. You can improve the optimization accuracy in many ways. For example, in this holographic case, we can incorporate more energy momentum data. We could promote the data that appear in the discontinuity to dynamical data and see if this kind of affects the optimization. The hope is to try and tune things to get better double twist data predictions on holographic CFTs, or maybe try and find some other calculation that can give us, for example, 1 point for the value of these tails. And then, as we saw in the GFF case, that seems to be very sort of fixing the solutions and giving you the right answer in that case. I made some assumption here that because I'm using a kind of meta heuristics, I'm running a large number of jobs, and my criterion is low loss and then small standard deviations. For stable solutions, these islands of stability, this is conjectural. It seems to be working relatively well, but it would be interesting to understand this a little bit better. And obviously, we would like to try and extend this to applications to zero temperature CFTs, theories with defects, boundaries, high point bootstrap, so on. So I'm a little bit early, but I don't think anyone complained about the talk finishing a little bit early ever. So thank you.
Any questions?
I wanted to ask, can you say again, you have this part where you put the discontinuity?
Yeah.
So what do you input to compute the discontinuity? How do you compute the discontinuity?
So you mean in practice, or that what enters the computation of discontinuity? So the way that you compute the discontinuity takes contribution from certain operators.
I mean, in your framework in which you're approximating the function,
Yeah.
how do you compute the approximate that we have?
So the discontinuity feeds into the approximation. So the discontinuity is not approximated; it's a thing.
I don't know the function, so I'm not understanding something very basic.
I see what you mean. Yeah. So you perform the expansion of the function in terms of thermal blocks,
Okay.
and then there you can see, for example, for generalized free fields, you know that nothing except from the identity contributes. So there is a general expression for what the double twist operators look like,
Yeah.
and you know that these things do not contribute. So for generalized free fields, it's just the identity, and you're happy and you're done.
Okay.
Likewise, so for the holographic CFTs, the spectrum is the identity, the double twist, which do not contribute, and then you have stress tensor and this kind of multi-stress tensor contributions, and then these things do contribute. So you say, I have one term from the whatever lowest stress tensor, for t squared, and then one from t, etc. So there you just compute these things explicitly. You can, and then you say, okay, this is an infinite series once again, right? And I have to truncate it somewhere. So I'm making some approximation to this discontinuity. And we went up to t equals 7. So one thing that you could try and do is see if you include more terms in that discontinuity, you get higher, better results. Now, one of the things that I didn't say explicitly here is that this kind of horrible kernel that multiplies the discontinuity has the effect of actually suppressing a lot of these terms. So this functional form is such that it suppresses a lot of these terms in cases where we could check.
But is there an idea that maybe because you have the low spin part,
Yep.
right? And then this, but could it be that if you feed the low spin part inside the sample, it's supposed to reproduce the high spin? What you're doing now is that now you're computing analytically somehow,
Correct,
right?
that's right.
Some framework.
Yeah, exactly. So this is exactly what I meant here. So dynamical discontinuities mean that you you have more contributions to discontinuity, which are unknowns, and these unknowns also appear as discrete data, for example.
Yes.
And then you update these things at each step of your
Yes.
optimization. So this is exactly what you say, and this is something that we could think of. Thanks.
Any more questions?
Just a quick question. In the case when you bootstrap truncating, in the
Can I do what
case
you're asking and come all the way there? So say again.
in the case when you bootstrap and you truncating,
Yep.
I just wanted to find out how do you choose your cutoff between the
It's arbitrary because we're not dropping anything. We say we're not truncating. We're converting terms in terms of discrete data, or then this contribution goes to the tail functions, or this contribution goes to the discontinuity. So nothing is dropped. And then there is a trade-off. Sometimes if you have, you put some terms in the discontinuity, the approximation of the discontinuity may not be as good. If you have more terms in terms of the tail functions, you have more functions to optimize over. If you have more discrete data, you have more discrete data to optimize over. So you're just kind of moving around the sort of difficulty of the problem of these degrees of freedom in that way without ever dropping anything. Does it make sense? Adrian has a question. Yeah, please.
So you have this like modeling this operating
Yeah.
system, right? But why do you only have that 0.5 references?
Why do you only have 5 double trace? So these correspond with high derivative gravities, and I think this is the dual spectrum, as it corresponds to things with scalar fields in the bulk and gravitons. Good. So I'm working at leading order and one over. I'm working at large C here.
But it's multiple T, what is the change at one
They might change, but I mean, I'm working the large and limits. Oh, I see what you mean. No, in this thermal case, actually, all these things are leading. So there is a discussion about how, in this thermal case, the n scaling of these things is different than what you expect at 0 temperature. It's actually a little bit tricky. So all these things are leading in one over n.
And how sensitive are your results? Your found the level lighting methods and you want to
How sensitive are they to what? To yes.
So how sensitive?
It didn't seem so. We tried a couple of cases, like for example, the dimension of the generalized free field. You mean? It didn't seem to make any difference in terms of. So you see, okay, in terms of how the spreads that we saw and the value of the loss, if they were comparable, the only thing that we would compare with something else in the literature was, and the reason why I chose here 1.5 is because these guys 5. So we just changed the number and ran it again, and this is what we got. But I don't think there's anything else to compare again. But in terms of performance, in terms of loss, how close is it to 0, and how small the spreads were, it was about the same. We could go, so at 0 temperature, you mean, or at 5? Yeah, it's one of the things that we're doing. Yeah, so we're trying to extend this to ON vector models of it.
Any more questions?
It's not a hard thing to do, it's just a become.
More? Okay, I'll just make a quick announcement before we thank Costas again. That we have a photo station now. I think Arnold will lead us outside the building. And let's thank Costas. And we'll again. We will meet at 11, right? So next we have the morning session is Robert Demilacos talking about secondary inheritance relations, terminals, and this Robert.
Thank you, Palab. Okay, so I'd like to start off by thanking the organizers. Actually, this Mandelstam School is always a highlight of the year for me. And I can tell you that everything that I'll be telling you at this Mandelstam 2026 started in conversations with Antal at the Rosebank Holiday Inn during Mandelstam 2025. So the meeting for me was actually very useful last year, and this one has also been great. Okay, so I worked with some really great collaborators. So as I said, the work started with Antal, then also Annemiek Gosch, who is a postdoc in Huzhou, Minkyu Kim, who was at Sogang University and now is at Seoul National University, Yaku, who's here, Gary, who's here, and Anik, who was a PhD student at WITS, and he will be starting a postdoc in Huzhou in March. Okay. So let me tell you what I want to talk about. So what is my goal? I want to explain how finite n trace relations modify the space of gauge invariant operators. Okay, if you're a student and you've never seen a trace relation, here's an equation that you see over here. This will be obeyed by any 2x2 matrix. And that's what the trace relations are like. They're equations that are obeyed, and they're just obeyed because of the dimension of the matrix and no other property. So that's an example of a trace relation. So I want to take a look at the space of gauge invariant operators, and the trace relations imply constraints on that space, and I want to solve those constraints completely. And then I want to talk about the answer when I've actually eliminated all of the trace relations, I've solved them all, I've got the smaller set of operators that are now free, they don't obey any relations. How do we describe that smaller set? And I'm going to show you that invariant theory gives us a very clean answer to that problem. So that's what I'd like to discuss. Well, the talk falls roughly into two parts. I'm going to motivate why finite n matters. I'm going to discuss multi-matrix quantum mechanics, although you'll see this also applies to systems of bosons with an SN symmetry, to vector models. So we'll be discussing these various models at various points as well. I want to introduce the key algebraic tools, so trace relations that give us the constraints, Hilbert series, which are very useful for counting. And then the main player is going to be the Hironaka decomposition. So this is a very crisp way to organize the space of gauge invariant operators. And it tells me if I want to generate it, I can generate it with two types of generators. There's something called a primary invariant, and I'm allowed to use these primary invariants freely. I can raise them to any power. And there's also some secondary invariants. And secondary invariants appear only linearly. Some other things I want to explain is the number of primaries goes like 1 plus d minus 1 times n squared for a model with d different matrices. And the number of secondaries grows like an order 1 number times n squared. I'll show you some concrete examples at small values of n and d. And this is roughly going to be the first half of the talk. And I will set up the idea that it's very important to understand the space of secondaries. And we've struggled to do that. In work in progress with Antal, we have now managed to figure out the space of secondaries by using a duality. And there's a duality between the secondary invariants of a bosonic vector model, so only the secondary invariants, and the states of a fermionic vector model. So I'll explain how that duality works. Good. Stop me at any time if you have questions, please. Okay. Some of you have heard something of this before. I promise you there will be something new for everyone. So, okay, so why should we be interested in finite n? So we know that 1 over n squared sets the strength of gravity. So at infinite n, your holographic dual is really a classical theory of gravity. You have some definite space-time. At finite n, that's no longer the case. You start to have to deal with quantum geometry. Another effect of finite n is that you have the stringy exclusion principle. And one of the things that I want to argue today is that we've never had a precise statement of the stringy exclusion principle. So I'll give you a precise statement today. Also, finite n is needed for black hole microstate counting. So we've just had this very nice series of lectures by Suk telling us all about fortuity. There you need to talk about properties of the operator at rank n and rank n plus 1. To have that kind of control, n has to be finite. It can be large, but you cannot take it off to infinity. And the operator trace relations become dynamical constraints on the emergent fields in the dual gravity. So it's interesting to understand and characterize precisely what these constraints are. So we'll be using matrix quantum mechanics. This is a very nice laboratory. At other times, we'll be using vector models and models with SN symmetry. So these models have dn squared degrees of freedom, but you must depend on them in a gauge invariant way. So that's an interesting constraint that you need to take into account. And I think for multi-matrices, we really have learned some genuinely new lessons, things we didn't know before. And another motivation for me that I'll be coming back to is that our loops, the traces of words, the gauge invariant operators, these are the dynamical variables in a collective field theory treatment. And that was a big motivation for this project, to try to obtain collective field theory descriptions for multi-matrix systems. So that we haven't achieved yet, but this is hopefully a step in the right direction. Okay. So I'm going to think about models with d Hermitian matrices XA. The index A goes from 1 to D. Each of the XA's transforms an adjoint of the UN gauge group. What are the gauge invariant operators? Build any word. That means the product of X's. And to state which word you've got, I'll just list the indices. And if you take the trace of that, that gives you something that's gauge invariant. So take the space of all possible single traces. And you're also allowed to take polynomials in those single traces. And that'll give you the space of gauge invariant operators. Now, there's a big difference between large n and finite n. At large n, all of these traces are independent, and your space of gauge invariant operators is just freely generated. At finite n, there are identities amongst the traces, trace relations. So you could imagine I take this massive set at finite n, there are all sorts of identities. I'll pick up a trace identity, eliminate an operator. Pick up the next trace identity, eliminate the operator. Keep going until I've used all of the trace relations. I'll be left with some smaller set, which there's no relations between those operators, and I want to understand the properties of that set. Let me just give you a little bit of a physical motivation why that question is interesting. And it really comes from a collective field theory type description. So what is collective field theory? So this was something put forward by Antal and Sakita. It offers a constructive approach to holography. So what do I mean by this? So you start from the CFT and you perform a change of variables to invariant variables. After you change to invariant variables, you might have to work hard to interpret the result, but the resulting theory is the dual gravitational theory. So what does collective field theory do? It performs a systematic reorganization of the dynamics. You move from gauge variant variables to invariant variables. That's what it's doing. A few things about this reorganization. After you've expressed things in terms of the invariant variables, 1 over n features as a loop expansion parameter. This matches the fact that 1 over n is g Newton, and g Newton is the loop expansion parameter of the dual gravitational theory. The change of variables features a Jacobian. This is very nonlinear. If you expand it out, you'll get an infinite set of interaction vertices. And in many examples, we can see that these interaction vertices precisely reproduce the interactions of gravity. And finally, the trace relations are visible as constraints that commute with the Hamiltonian. So it makes sense to take the Hilbert space of all of these operators to impose the trace relations, and then you're learning something about the space on which the collective field theory is defined. Just to give you some evidence where it has been successfully applied. So maybe the first example was the C is equal to 1 string with the Dasyevitsky string field theory for the C is equal to 1 string. Anything calculated with the Dasyevitsky string field theory agrees perfectly with other approaches to this low dimensional strings. Also for higher spin gravity, Dasyevitsky proposed a model based on bilocals. I would say for that model, it's very well developed, and you can precisely reproduce all of the features of a completely gauge fixed gravity description. But we really hit the gravity description on the nose. Many checks have been done. This has been done to look at duals to higher spin gravity in DS in terms of symplectic fermion vector models. That's not so well developed, but it's an interesting idea. Together with Joao and Antal, we wrote down a string field theory in the ADS5 PP wave. And again, you reproduce precisely the cubic vertices of string field theory through this method. And finally, in SYK, Antal, together with Kenta Suzuki and Jungi Yoon, have written down a gravitational dual to SYK. So this is actually one of my big motivations. This is why we started on this project. Okay, so the constraints come from trace relations. Suk gave us a nice description of the trace relations yesterday. You may have heard them also in Antal's talk and Joao's talk, but let me just go through them again. This is the central constraints that we're trying to impose. And what we're using is some results by Procesi in the 70s. Procesi was an invariant theorist, a mathematician. Procesi said if you want to describe the trace relations at n is equal to 2, for example, pick up 3 matrices, W1, W2, W3. They're each 2 by 2 matrices, and anti-symmetrize the column indices. There's 3 column indices. There's 6 ways of permuting 3 objects, which is why there's 6 terms in that equation. We're anti-symmetrizing, so 3 of the terms are negative, 3 of the terms are positive. That sum has to vanish because this collection of terms was obtained by anti-symmetrizing 3 indices, which each take 2 values. Well, you'll always get 0. You'll get 0 for every value of I1, I2, and I3. Procesi then instructs us to sum over I1, I2, and I3. We still get 0 because we're just summing zeros, but we land up getting an identity between the traces. And what the bulk of Procesi's theorem is proving is that this identity is universal. Meaning, if you specify W1, W2, and W3 to specific words, you generate the complete set of trace relations. Now, he didn't prove it for n is 2, he proved it for n by n. So you should take n plus 1 of these matrices, anti-symmetrize the indices, anti-symmetrizing n plus 1 indices, which each take n values, again gives 0. And again, the resulting identity is universal. It produces the complete set of trace relations for the matrix models. Now, I should say for vector models, I'll show you how this exact argument gives you the complete set of trace relations for the vector model. And if you were dealing with a model that had SN symmetry, again, these are the universal identities. For the SN case, you would take diagonal matrices. For the SN case, this was proved in mathematics by Demokos. For the vector model case, it's something that we have observed, but it's using exactly the same logic. And when we get to the vector, I'll explain that. Okay. So now that we understand the constraints that we're trying to solve, we would like to make a link to invariant theory. So how do we do that? We're going to calculate a specific observable of the algebra. It's a property of the algebra. It's called the Hilbert series. And when you see the Hilbert series takes a specific structure, invariant theory immediately tells you a lot about the algebra just by looking at the Hilbert series. So to calculate the Hilbert series, we're going to evaluate a matrix oscillator, the partition function. It's the usual thing. It's a sum over states. And for each state, we weight things by e to the minus beta times the energy of the state. Beta is the inverse temperature. And I'll also think about the partition function as a function of x, where x is equal to e to the minus beta. This is an oscillator, so I can diagonalize it as usual with creation operators. So if I want to write down oscillator state with energy E is equal to n, I will apply a total of n oscillators to the vacuum. I want the gauge invariant state, so I need to contract all indices. It could have been a single trace. It can be any complicated multi-trace. The thing that's important here is I'm starting to look at words in the A daggers and take traces. So these are the invariants of the space. So what we see, for every invariant, we have a state, and for every state, we have an invariant. There's actually a one-to-one map between states of the oscillator and invariants. Also, the trace relations become a statement that some of the oscillator states become null. Those do not contribute to the partition function. So this map between invariants and states is invariance after the trace relations have been solved. So that's why this is such an interesting observable. More than that, if we take a look at the energy of the state, well, this is an energy E is equal to n because I've subtracted off the ground state energy. And what is n? Well, that's just the degree of the invariant. So if I take a look at my partition function, the sum over states become a sum over invariants, and I weight each invariant by x to the degree of the invariant. That is precisely the definition of the Hilbert series. So if we calculate this matrix oscillator partition function, we're getting hold of the Hilbert series, which is a property of this algebra after the trace relations have been solved. That's why it's so interesting. These Hilbert series take a very specific form. What they look like, they're a rational function. The numerator of that rational function is a polynomial, and all of these CIS's are positive integers. And then we've got a product of factors, 1 minus x to the j sitting in the denominator. So that's what the partition function looks like. The Hilbert series. You tell an invariant theorist, this is the Hilbert series of my algebra, and they'll tell you the following. For each factor in the denominator, there is an operator called a primary invariant. The factor 1 minus x to the j, this x to the j is telling us that this primary invariant is degree j. So there's a total of j matrices multiplied. It's a single trace term. It might be a sum of single trace terms. Each term being summed as single trace, each term has degree j. An invariant theorist will also tell you that each monomial in the numerator is associated to a secondary invariant. Secondary invariants can have an arbitrarily complicated multi-trace structure. They can be a sum of terms, and each term can have a different multi-trace structure. X to the I corresponds to an operator of degree I. So there's a total of I x's multiplied in. And then the final thing that invariant theory tells you is every single gauge invariant operator in your theory can be written as an expression which is linear in the secondary invariants with coefficients that are arbitrary polynomials in the primary invariants. So that's what the space looks like. Every single gauge invariant operator in this theory can be written in this way. And if you take the primaries and the secondaries together, they are free. There are no relations between them. And if you generate the space, it's completely free. The trace relations have been solved. Now, this structure is extremely suggestive. So this statement is a fact. You cannot have a problem with it. It is a theorem. It's just a fact. But we want to interpret that. Imagine you have a theory with solitons, for example. You could have a no soliton state, a one soliton state, two soliton state, and so on. So your whole Hilbert space will be written as a direct sum over states with different soliton numbers. And in each non-perturbative sector, you can act with A daggers and add some perturbative excitations to that state. Well, this is exactly the structure that we've got. We've got these direct sums. Each term has a single secondary invariant, and we're allowed to dress it up with the primary invariants raised to any power. So our interpretation is that the primary invariants correspond to perturbative degrees of freedom, while the secondary invariants correspond to non-perturbative degrees of freedom. That's almost correct. There's just one small subtlety, and I'll be mentioning that soon. Okay.
If you multiply more than two secondaries, you expand it into the primary.
Exactly, and we'll see exactly that identity. Absolutely. So why can't you take secondary squared? We'll see why not. Okay. So here's an example. Two matrices, n is 2. Go ahead, calculate the partition function. That's what it looks like. How do you think about that? There's 5 factors in the denominator, which means 5 primary invariants. 2 of them are degree 1, but for 2 matrices, they are unique 2 invariants of degree 1. 3 of them are degree 2. Again, we know exactly what those are. They couldn't be anything else. Those are the only 3 degree 2 invariants. And there's only a trivial secondary invariant. So what did we prove? So we proved an inductive argument. It was an inductive proof that proved the following. Pick up your most general gauge invariant operator. So trace of any word, any length, product of multi-trace operators, you can give an inductive proof that this most general gauge invariant operator can be written as a polynomial in these 5 invariants. So that you can prove by induction. What's the equation that you're continually using? The trace relation. And the only thing you have to be clever about is choosing A, B, and C correctly, so that after using a sequence of trace relations, your gauge invariant operator is always just a polynomial in those 5. If you had a single matrix, and I said to you, what's the simplest way to describe the gauge invariant degrees of freedom? You would have said it's just the eigenvalues. Well, what you can see here is M1 and M3 together. This is the trace of x1, which is the sum of the eigenvalues, the trace of x1 squared, the sum of the eigenvalues squared. So if I tell you these 2 pieces of data, I've told you the eigenvalues of x1. If I give you M2 and M5, well, now I've told you the eigenvalues of x2. But x1 and x2 cannot be simultaneously diagonalized. And that's why we need one more piece of data, trace x1, x2. But I think that before we did this, we certainly didn't expect such a simple answer. This is a beautifully simple answer that everything is generated by these 5 primary invariants. Okay, let's do another example. This is 3 matrices with n is equal to 2. This answer is particularly interesting because we get some non-trivial secondary invariants. If you look at that partition function, there's 9 factors in the denominator, which means there must be 9 primary invariants. And again, it's absolutely unique. There are only 3 degree 1 invariants, and there are only 6 degree 2 invariants. So we know exactly what those are. When you look at the numerator, you know that there's 1 secondary, trivial secondary, 1 corresponding to that 1. And then there should be another, oh, sorry, this should be an x cubed. Okay, this actually is an x cubed. There's 1 secondary of degree 3. And when you look at that secondary of degree 3, you have some choice. If you choose the trace of x1, x2, x3, that's perfectly good. If you choose the trace of x1, x3, x2, that's perfectly good. If you take a linear combination of those 2, that's also perfectly good. So there's some freedom in choosing your secondaries. You're not pinned to choosing a specific secondary. And again, using the trace relations, we gave an inductive proof that the most general operator, gauge invariant operator in this theory, can be written as a linear combination, S1 times the polynomial in the primaries, plus S2 times the polynomial in the primaries. So again, that's a complete description of the space, and you only use S1 and S2 linearly. Now, primary invariants act freely. You can raise them to any power. Secondary invariants appear at most quadratically. Why? What's happening? That's also being driven by the trace relations. So by using the trace relations and a little bit of stubbornness, you can prove this equation. And what it tells you is S2 squared plus something linear in the secondaries with coefficients that are polynomials in the primaries is equal to 0. And that means if you have kept everything that is linear in the secondaries with polynomials in the primaries, you should not add S2 squared. You've already got it. So, and this is a general statement, again, coming from invariant theory, that a product of 2 secondaries can always be written as something linear in the secondaries times a polynomial in the primaries. And that's why we only include things linear in the secondaries. I keep saying invariant theory tells us this. What is it in invariant theory that we're using? We're using something called the Hironaka decomposition. If your algebra of operators admits a Hironaka decomposition, the Hilbert series will always take this form. this language that the primary invariants are encoded in the denominator and the secondary invariants in the numerator. This is part of the machinery of the Hironaka decomposition. The number of primary invariants, which is the number of denominator factors, is called the Kroll dimension of the ring. That's the maximum number of linearly independent elements. There's a very nice way to calculate the Kroll dimension of all of these rings. Do a complete gauge fixing and count how many degrees of freedom remain. And that gives you the Kroll dimension. So that would be a physicist's way of calculating the Kroll dimension. But if your Hilbert series takes the Hironaka form, that's necessary, but not sufficient for it to admit a Hironaka decomposition. So we know of rings which do not admit a Hironaka decomposition, but still have a Hilbert series of that form. So why are we so sure that our algebra admits a Hironaka decomposition? We're relying on two powerful theorems. The first one is the Rochester-Roberts theorem. What the Rochester-Roberts theorem says is, if you're studying the invariance of a linearly reductive group over a field of characteristic 0, your algebra of invariance is Cohen-Macaulay. And there's a second theorem which tells us that if your algebra is Cohen-Macaulay, it admits a Hironaka decomposition. But let's just unpack this a little bit, because these are maybe words that are not familiar. I didn't know what they meant before we started this project. So when we, yes. Okay, so what is a ring? You can think that a ring is a generalization of a field, and now it's the primaries themselves that generate that. So imagine taking polynomials and all possible primaries. That's a ring. Yep. I also say algebra because some of these structures that we consider are slightly more general. So if you should think that rings are a generalization of fields. If you have a vector space, you would have a coefficient. Maybe you'll have I hat, a coefficient j hat, a coefficient k hat. And if A, B, and C belong to the reals, this would be a three-dimensional vector space defined over the reals. In this situation, what we have got is we've got three coefficients, fa, fb, fc. These all belong to the ring generated by the primaries. And then we have some secondary operators, O1, O2, O3, plus, plus. This is what we're studying. And you can see the fact that we keep these only linearly is just like the fact that we keep these vectors only linearly. So this is a generalization of a vector space. So this is called a module. The secondaries are the basis of that module. And this module is defined over the ring generated by the primaries. So that's why I won't always say ring. Sometimes I'll say algebra so that I include free modules. Yeah. So the first theorem that we're using is called the Rochester-Roberts theorem. So I was about to tell you what we mean by a linearly reductive group. If you have a linearly reductive group, here's a test. Pick any finite dimensional representation. Is it completely reducible? Then your group is linearly reductive. So all of the groups that we like in physics, SON, SPN, UN, SUN, they're all linearly reductive. So the story that I'm telling you today is very general. And we've checked it for vector models, tensor models, bifundamentals, mixed matrix vector, all of them admit Hironaka decomposition. What does it mean to be Cohen-Macaulay? The simplest kinds of algebras are the ones for which their generators don't obey any constraints. For those, because the generators are really independent, there are many nice theorems that you can prove. One of the theorems you can prove for free algebras is that they admit Hironaka decomposition. You can think that the set of Cohen-Macaulay algebras is the biggest set that generalizes the properties of a free algebra. So they all enjoy the properties of free algebra. So every free algebra is Cohen-Macaulay, but not every Cohen-Macaulay algebra is free. So this is a generalization of free algebras that enjoys the properties of free algebras. Okay, so math, yep.
Can I ask, so I missed one step. So how do you compute the z of x?
Okay, good. It's a matrix partition function. So I invite you to use your favorite method. Let me tell you my favorite method. I use the Molinois formula. So it's a concrete formula. It amounts to doing n integrals over unit circles. So much the same way as people compute indices, I just go ahead and use Cauchy's theorem.
But did you specify some specific Hamiltonian? Sorry, I missed.
Oh, I always use the harmonic oscillator because it's the oscillator that gives me the Hilbert series. Yeah, and then I'm getting a property of the algebra, no matter what interaction you've picked and what coupling strengths. Yeah, okay.
Understand, can I understand this core dimension as it's counting the number of matrix elements subject to gauge fixing?
Absolutely.
Yeah.
Yeah, and
N square plus matrix element, N square minus.
absolutely. So you would think that you've got a UN symmetry, so you can subtract n squared, but in the adjoint, the overall U1 never operates. So that's where that formula comes from. You can also calculate the Krull dimension for vector models or mixed matrix vector models, and the same argument gives you exactly the Krull dimension. Yep. So mathematicians know nicely. Yes, sorry, Kostas?
Could you just elaborate a little bit on why you identified the secondary variants with non-perturbative states? Because I mean, to me, it seems that the guys needs different vacuum, but if they're making a box space over, and we understand the vacuum have to do with solid line or
Yeah.
sets and non-perturbative stuff, but those are perturbatively different.
So I'm thinking, you know, I'm imagining that I have a unique vacuum. I have and maybe this is empty. I have a unique 1 soliton state. I have a unique 2 soliton state, and so on.
But let's say string theory could have twisted sectors, right?
Yes.
Theory. That's perturbative.
Uh,
Would have this structure, I would say.
yeah.
On each sector defined by some group element of the discrete group, you could start.
So that you would add to this discussion, you know, that would be an extra set of sectors, which is okay. But
Because I'll show you in this case why they are non-perturbative, but as Antal said, you could just add to those. And in fact, we will see that not every secondary, in fact, is non-perturbative. So I said I will need to revise the statement slightly. There's some small qualifier, but I'll tell you what that is.
Yeah. Show some examples from ADCFT where you can make this matching, for example.
I'm always in quantum mechanics for now. Oh, yeah. Okay. Okay, so here is an example where we know the Krull dimension. Mathematicians have calculated it, but they have no idea about the number of secondaries. So we wanted to figure out something about the secondaries. And following the kind of philosophy that Costis outlined yesterday, that it's good to have data, we also generated some data. What we did was we calculated partition functions for n going from 2 to 7 for a 2 matrix model. In this case, what should the Krull dimension be? Just 1 plus n squared. And we generated it for n, going from 2 to 7. So for example, at n is 5, we get some partition function. How many factors does it have in the denominator? 26, and that's 5 squared plus 1, which is great. And then we just read off how many secondary invariants do you have. So look at the primaries. They increase modestly from 5 to 50. How do the secondaries increase? Well, it goes 1, 2, 64, 15,000, 312 million, 21,000 billion. And that's much faster than a power. If you try to fit a curve to that, it looks like the exponential of an order 1 number times n squared. That's what it looks like. Can you prove that? Actually, yes, you can. The way that we proved it is as follows. We went back to 2 matrices and we solved the harmonic oscillator problem exactly. The eigenstates of the harmonic oscillator are given by restricted Schur polynomials. If you're looking at a state constructed using n A1 daggers and m A2 daggers, it's labeled by 5 labels. 3 of them are Young diagrams. 1 has n plus m boxes, 1 has n boxes, and 1 has m boxes. Now, these states of the oscillator are highly degenerate, but you can introduce a label that resolves this degeneracy. These multiplicity labels are called alpha and beta, and they go from 1 to the little Wood-Richardson number. So if you calculate the partition function, you get a little Wood-Richardson number squared from summing over alpha and beta, and then you still have to sum over the Young diagram labels. Why is this a useful rewriting of the partition function? In 2019, mathematicians calculated the biggest little Wood-Richardson number. If n, m, and n plus m scale like alpha n squared, the biggest little Wood-Richardson number is e to the alpha n squared over 2 log 2. So what we did was we said, let's get a lower bound for the partition function. And the lower bound for the partition function was obtained by just summing the biggest term. So now we've got a lower bound for the partition function. Now let's look at the primaries and let's get an upper bound for the contribution from the primaries. Now, if you remember, the contribution of the primaries is just a product over J 1 over 1 minus x to the j. So working out this partition function is a problem of calculating partitions, and the combinatorics for that is very well developed. So we've got a lower bound for the partition function. We were able to figure out an upper bound for the contribution from the primaries, and there was a massive gap. That gap has to be supplied by the secondaries. So in that way, we were able to argue that the number of secondaries must grow as e to an order 1 number times n squared. And the only way to get that many different operators is if the secondaries are built using order n squared fields. So the secondary invariance, almost every secondary invariant is a very heavy operator built using order n squared fields. Now, if you think back to the half BPS sector in n is equal to 4 super Yang-Mills, where things have been solved in a lot of detail, operators were built using order n squared fields correspond to LLM geometries. These are operators with such a big conformal dimension that you can't ignore back reaction and you actually get a new space-time background. So that fits nicely with our proposed interpretation that these correspond to new space-time backgrounds. Yep.
In the large n case, is there a notion that secondary operators are heavy? Their energy scaling in n or something?
Yes. So over here, what I've shown you basically is that almost every secondary has an energy of order n squared. If you really take n to infinity, all of these guys decouple, and in the strict n is equal to infinity limit, it becomes just free. All of the secondaries are gone. Yeah. Okay, and this also looks very similar to what Suk was telling us about the fortuity mechanism. Because in that situation, you had an operator that at low values of n was a 1/16 BPS black hole state, but as you increase the rank, it fails to be a 1/16 BPS black hole state. So the character of that operator changes. Here too, at low values of n, an operator is secondary, but if you raise n, it will always transition to become a primary. In the case of fortuity, the way this happens, you rely crucially on the trace relations. In the case of primary and secondary, this classification relies crucially on the trace relations. So I think that there's many reasons to suspect that there's some relation between these two concepts. It would be nice to make that more precise. We haven't managed to do so yet. Okay, so now.
Robert, one question.
Yes.
Previous slide.
Yep.
Is D given something that for
D? Yes.
D.
Take the log 2 and replace it by log D. Yep. So it's always an n squared growth. It'll be for any D matrix model. Yep. Okay. So now, let me come back to the statement that I said that not every secondary can be considered as a background. What is the loophole? So we know that the number of primaries is the Krull dimension. So that's a fact. Now, let me tell you another fact. If you look at the single trace operators with n or fewer matrices inside the trace, those have to be included amongst your generating invariants, because the trace relations only kick in when you've got n plus 1 matrices inside the trace. So n matrices or fewer must be amongst your generating invariants. How many of those single trace operators are there? Well, if you look at operators with a length of order n, this grows exponentially with n. And that's a much more rapid growth in the number of primaries, which is only growing like n squared. So for reasonable values of n, most of these invariants that you have to include must be included as secondaries, but they're short, they're not long, they're not new backgrounds. So here's an example with a 2-matrix model at n is equal to 20. If you count the total number of single trace operators using polio counting, there's 111,321 of them. How many primary invariants are there? 401. So already just for 2 matrices at n is equal to 20, less than 0.5% of the invariants are primaries. You need to include more than 99.5% of them as secondaries. So we have to think about what these small secondaries mean, and we'll talk about that in a minute. But let me just point out that we are getting here quite a big revision of the stringy exclusion principle. The stringy exclusion principle, the most naive statement that you would often see peddled, is that if you take a trace of n matrices or fewer, you include those variables, And everything with more than n matrices in the trace, you discard because they can be generated by trace relations. Actually, that's a very rough statement. Here we're saying there's a small fraction of single trace operators that you use freely, a much bigger fraction of single trace operators that you use just once, you only use them linearly. And if you actually look at the spectrum of the primaries, there are always some primaries with more than n matrices inside the trace. So you cannot cut off at n. And there's an even bigger revision. So let me discuss that now. So to actually figure out what do these small secondaries mean, we looked at models where we could construct lists of secondaries. We first of all looked at a matrix model with 2 matrices at n is equal to 4. That was a very complicated analysis. And then we looked at models with SN symmetry, where we could very explicitly construct these lists of secondaries. And what you find is these secondaries take 2 forms. There are some that we call irreducible secondaries. They are a single trace operator with fewer than n matrices inside the trace. And there were also irreducible secondaries. So you construct the list of secondaries, and some of them look like you've taken the single trace secondaries and raised them to some power. Because this list is finite, on that list there's always a maximum power for the single trace that you can get up to. Thinking in ADS-CFT, a multi-trace state corresponds to a multi-particle state. So this cutoff on these powers over here are actually a cutoff on the graviton occupation numbers, the occupation numbers of KK gravitons. So I think that we are all familiar with the statement that the string exclusion principle cuts off the momentum of a sphere giant graviton. Actually, the string exclusion principle cuts off the occupation number of just normal KK gravitons. So it's operating here as well. And why does it get cut off? It's not that that state is not there. That state is there, but it's redundant with some other state that you've called. So this cutoff that you're seeing now, even on the KK graviton occupation numbers, is due to the redundancy of gravity, as coded in by the trace relations. Okay, so that was the first half. So now let me get to the second half and tell you what we were trying to do here. We really want to find a case where we can count the number of secondaries and relate that to an honest black hole entropy. So we're interested in studying something like the BMN matrix model, where we know in the gravity dual there are black holes, and we would like to reproduce that entropy by taking the log of the number of secondaries. What do we have to do that? Well, it's not good enough to just know the total number of secondaries. From our partition function, we're being told the total number of secondaries. What we would like to do, we'd like to say, here's a black hole with these global charges, and then we'd like to count the number of secondaries with those global charges. It's not good enough to just know the total number of secondaries. Even calculating the total number of secondaries, that partition function with n is equal to 7 took more than a week to run on my laptop. 15 minutes, great. It took more than a week to run on my laptop. Actually, people who do indices told me when you're calculating some index, it can take an equally long time to run. So we wanted to find methods to get hold of the secondaries more efficiently. So Sam might have some good ideas in his talk. I think that he might also have something to say on this problem. The way that we addressed it is we've discovered a duality operating at the level of vector models, and this duality relates the secondary invariance of the bosonic model, so just the secondary invariance, to the states in a fermionic Hilbert space. So there's a duality between those two. Yep.
So I understand the counting you want to do is for supersymmetric black holes, or is it finite temperature?
I would be happy with either. So BMN black holes are only known numerically, but there are solutions that are known. I would like to reproduce the entropy of those. Here, I'm not specifically tied to SUSY. If I can really get hold of the secondaries and count them, I should be fine. Yeah. Okay.
And what? Since the secondaries only act linearly, I mean, couldn't we have guessed from the beginning that they would be related to some fermionic operators?
Yeah. Seems so suggestive, right? So now we're realizing that logic. Yep. Yeah.
So, but you're realizing that for vector models, is that right? Is there any indication that something like that could also be realized in matrix models?
In progress. Yeah. Okay. And I'll explain to you how the duality is working. I mean, there's something very suggestive about it. So for the bosonic model, what are we going to do? This is our color invariant variable. We sum over I, that's the color index. our bilinear transforms an adjoint of the UF flavor group. And what is our ring given by? It's just the matrix elements of this matrix, and we need to impose a constraint which is rank of m is less than or equal to n. And I'll show you that this actually agrees with Procesi's description of the trace relations. When you calculate the Hilbert series, evaluating the numerator at x is equal to y is equal to 1, you get the number of secondaries. And with Annemiek and Jaco, we calculated the number of secondaries, and that's a closed formula for the number of secondaries. Okay, now let's go to the fermionic model. So we're going to consider k fermions in the fundamental and k in the anti-fundamental of UN. And we again just calculate the partition function using something like Moline-Weil. And we get a dimension for the Hilbert space. So there's a dimension for the Hilbert space. It's just a partition function evaluated at 1. And what is this Hilbert space? It's counting the number of states that is created by this fermion bilinear. That's what it's actually counting, and you'll see that very explicitly. And the remarkable fact is, if you compare the number of secondaries, it's exactly equal to the dimension of that fermionic Hilbert space. And in fact, I'm going to argue to you that this is not an accident. These are two presentations of one underlying representation theoretic object, just written in two different languages. The language of the bosonic invariants, the language of the fermionic singlets. And the other thing that's very interesting is that when you get the trace relations in the bosonic model, so these are some constraints that have to be imposed, some of those trace relations become trace relations in the fermionic model, but some of those trace relations become equations that are true just because you've got fermions. So there's a nice mapping between the constraints of the two sides. Some of them now become just Grassmann constraints, and others are mapping trace relations to trace relations. The other thing that's interesting is, notice that the number of flavors in the fermionic model is the number of bosonic flavors minus n. So we're dealing with smaller matrices in the fermionic case. So the number of trace relations is reduced. The extra trace relations are provided by the Grassmann conditions. So that they...
Just a little bit confused. These are not the matrix indices that you're talking about here are not gauged, right?
Yes, that's right.
You're gauging them.
No, I'm not gauging them. So these are not gauged at all. So you might wonder, where do the trace relations come from? I'll address that. So the trace relations will have to do with the I index, the indices of this matrix with the alpha beta. So I will tell you the relation between those two. Okay. So,
there must be a previous slide. There must be a constraint. There is a constraint between f and n.
yes.
Because k must be
F is greater than or equal to n. That's right.
That is, so in the large n limit, what would that mean? Like we need a large number of flavors?
Absolutely. So we're always working at finite n. If you wanted to take this all the way to n is equal to infinity, the number of flavors must always be greater than the number of colors.
Setting, what would that mean?
Well, so the way I'm thinking about this in a holographic setting, and I don't know if this will be the only application, I want to think about a model of fermions, say a field theory. I want to stick it on a lattice. And this would be saying the number of lattice sites is always much bigger than the number of colors. That seems reasonable. Yeah. Okay, so this is our bosonic bilinear. It transforms an adjoint of the U3 flavor group. What is our ring? It's generated by MAB subject to relations. And the relations are that the rank of M is less than or equal to 2. So it's really that the determinant of M is equal to 0. Now, this determinant of M equal to 0 looks like it's relating to the flavor indices. So coming back to Sam's question, how does this connect to the trace relations as they were described by Procesi? And it connects as follows. So we can define 9 2x2 matrices. So for every choice of the flavor indices A and B, we get a matrix. And it's just phi AI, phi BJ, dagger. And we've now got a matrix on the IJ indices that is a 2x2 matrix, but there's 9 2x2 matrices. And now you can build words, A, B, and C out of these matrices, K, A, Bs, and you can get a bunch of trace relations. Let me show you these two descriptions are equivalent because it really wasn't obvious to us when we started. This expression for the Moline-Weil formula is obtained by using the usual thing, using Procesi's description of the trace relations and going ahead and calculating the partition function. If we use this description, well, MAB has got a total of 9 matrix elements. So in the Hilbert series, we have a 1 minus t to the 9. Each of the MABs are degree 1. And then we have one constraint, which is that the det of M is equal to 0. And that's a constraint at t cubed. And if you divide 1 minus t out of the numerator and 1 minus t out of the denominator, you get the answer that you would from Procesi's description. So that's the proof that we can either think of the trace relations as Procesi did, or we can think about it as det M is equal to 0. Yes, Anosh?
Why 9? Why 9 matrices?
Because A runs from 1 to 3 and B runs from 1 to 3. That's the flavors. Yeah. Okay. And now we want to construct the secondary and primary invariants. So we separate this matrix M into its trace and its traceless pieces. The primary invariants are given by the traceless pieces. The secondary invariants are given as 1 tau tau squared in terms of the trace of M. And to show you that this is a correct description of the invariants, this equation over here is the equation that det M is equal to 0. And this is the relation that tells you that the product of these two secondaries can be expressed linearly in terms of the secondaries. So that's the quadratic relation that proves it. Tau times tau would trivially be tau squared. 1 times tau would trivially be tau. So all of the quadratic relations are trivial except for the tau times tau squared. And that comes from det M is equal to 0. The other thing that we have done is we generated the space based on the primaries and the secondaries. We can verify that that space is free. There are no relations between the resulting operators. And we have also verified that up to total degree 12, we were able to generate all gauge invariant operators using that basis. So numerically, we've checked this is a good set of primary and secondary invariants. Now let's look at the fermionic model. So in the fermionic model, we've got a single bilinear. And if we take a look at this, J has got a psi dagger and a psi. So J to the K would include K psi daggers, K psis. We've got a total of 4 independent psi and psi daggers, so the J cubed vanishes. Now, in the bosonic model, J cubed was eliminated because of a trace relation. In the fermionic model, J cubed is eliminated just by a Grassmann condition. So that's the simplest example where you see a trace relation being replaced by a Grassmann condition. And so there's an equality actually of these states, exactly how they transform under the flavor group. And this is just an example of something much more general. I'll just show you one more example. This is when n is 2 and f is equal to 4. In this situation, this is what our invariant looks like. There are a set of trace relations. It's the ideal of all 3 by 3 minors. And when you calculate the Moline-Weil formula, you find there are 20 secondaries, and they've got some very non-trivial degrees. So this is an example where things really are quite non-trivial. And let me show you how it works. So the fermion model is going to have a U2 flavor. So what we've done is we've separated these 4 flavor indices into one set 1, 2, one set 3, 4, and we broke M into 4 2 by 2 blocks. In this model, there's a total of 12 primary invariants, and the number of matrix elements in the blue blocks is 12. And it turns out that the primary invariants can be given as the matrix element in the blue block shifted by x1, x2, x3, x4, and x1, x2, x3, x4 are the matrix elements of this red block D. So we're building the primaries out of the blue blocks, shifting by the red block, and this red block, which transforms in the adjoint of a U2 flavor group, that's actually going to be identified with the fermionic fields. So that's how the duality will work. Why did I choose these specific primaries? There's 2 reasons. So to get the right flavor transformation, also we know that the primary invariants are free. If you set all of the primary invariants to 0, you get something called the covariant algebra. And this, after you've imposed the trace relations, should give you a basis for the secondaries. And we know what that basis should look like from the Moline-Weil function. So we must get this sort of a basis. So that's a check to do. And so setting all of these primaries to 0 determines all of the blue matrix elements in terms of the red ones. So you get some matrix with x1, x2, x3, x4s. All of the matrix elements are linear in the x's. Okay, so what are the relations we have to impose? Well, we have to ask that all 3 by 3 minors vanish. What does that mean? Pick a matrix. So you want 3 row indices, 3 column indices. And to choose 3 indices, you've got some choices. You could pick 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. And you could use this choice independently for the row and the column. You get a total of 16 identities. If you take those identities, they're all cubic. So now we want to know what are the independent things we can make out of x1, x2, x3. Well, at degree 0, it's just 1. At degree 1, it's just everything you can make. At degree 2, it's just everything that you can make. At degree 3, you have to solve the constraints coming from the minors. So I've just written the solution for the constraints, not too important, except to note the following. The only cubic terms that are not determined are x1, x2, x3, x1, x2, x4, x1, x3, x4, and x2, x3, x4. So this is detail that is coded into the trace relations of the bosonic matrices. The other thing, the terms that I've coded in black, those terms will vanish on the fermion side because of the Grassmann property. It will be some square of Grassmann numbers. The red terms will correspond to trace relations in the fermion model. So of the 16 trace relations that you get in the bosonic model, 12 of them become Grassmann conditions, and 4 of them are trace relations for the fermions. Okay, so 5 minutes. Okay, good. So in the end, when you solve them, if you solve the trace relations, those are the secondaries you get. We again check that this is the correct structure in the sense that you generate only a free space, so multiplying things linear in secondaries with coefficients that are arbitrary in the primaries. There's no relations amongst those operators, and we're able to generate all gauge invariant operators. Again, we check up to degree 12. So this is a good set of primary and secondary invariants. When it comes to study, okay, so this is a proof that actually those 3 by 3 minors vanishing agrees with the trace relations. So I won't go through that. That is quite nice, but let's just skip that. So if you go to the fermionic model now, this is what you've got. So we've got n is 2 and the flavors 2, so alpha and beta also go over 1 and 2. So our fermionic bilinear is a 2 by 2 matrix. I've called it x1, x2, x3 with these tildes in what I hope is a suggestive language. And what you see is if you just use, so at degree 0, degree 1, degree 2, there's no constraints. So we can build exactly what we had for the bosons. At degree 3, there's 8 possible cubic terms left after you impose the Grassmann relations. So the Grassmann relations have killed 12 terms. That was done by trace relations on the bosonic side. If you then look at the trace relations in this model, that's what the trace relations look like. And they eliminate x1 squared x4 tilde, x4 squared x1 tilde, x3 squared x2 tilde, x2 squared x3 tilde. So at degree 3, we get exactly the same invariance that we had from the bosons. And if you go to degree 4, there's only one thing you can write down, and it's exactly what you had from the bosons. So here's an example where you see actually the states of the fermionic model exactly match to the states of the bosonic secondaries. So this is a duality between the secondaries of the bosonic model and the states of this fermionic Hilbert space. It carries on at higher F and N, but the details become more complicated. So we're optimistic. So this is the first step, but we want to find the duality that's operating for matrix models and then count the number of secondaries in the matrix model, secondaries that have specific global charges, take the log of that and try to reproduce now an entropy of one of these black holes in the BMN matrix model. And that would be quite a careful check that the secondaries really are corresponding to microstates of the black hole. And I will stop there. Oh, sorry, wrong one. Good.
Trigonometric quantification, which was the topic of first part. But the integral formula which use is Taylor series, and we formulated in terms of volume. You are aware of?
Yes, yes.
summing up the Thomas this transformation becomes formula for that, and reformulates and use that to clarify spatialism like approach. Do you think
Yeah.
that's useful?
Maybe, I don't know. So when it's reformulated, you see, the duality here is just between the secondary invariants. It's not that everything is playing a role in duality, it's just the secondaries, which is maybe a bit surprising. I guess when Samir has reformulated, everything is a fermion.
Yeah.
So that felt like it was a bit of a difference. Yeah.
Any more questions? Is it perhaps possible to find some generating functions with the secondary division? It seems now it's just at every end, you just have these numbers. But is there some function that's apart from doing it exclusively?
So we did take the sequences we had and asked OEIS if it recognizes it. It doesn't. And then we were looking, what do mathematicians know about secondaries? And the most efficient algorithms to construct secondaries involve group bases. So for example, when somebody manages to construct the secondary invariants for two 4x4 matrices, that will be a paper in math, and they'll just say what the invariants are. So I would say that there aren't efficient algorithms to construct the secondaries. And then as far as counting goes, Hironaka only works if you grade by degree. If you try to use a finer grading, you're not guaranteed that you'll get Hironaka form. And it's basically because the primaries don't respect a finer grading.
I guess a follow-up maybe question. I mean, I guess I'm asking because I'm kind of confused by the statement that each secondary acts only once, because you're identifying them with maybe some soliton states, but I can't kind of think of two soliton states as a one soliton acting twice, right?
So there are.
So I guess you can take some long limiter with it becomes two solitons. So if you had a generating function, you could tell me, well, actually these come from the same one, but acting multiple times.
Absolutely. So I think that structure that you're thinking about, we actually see that structure. And it comes when we constructed lists of secondaries for the SN model. And there you really see, so this would look like it's a multi-particle state built out of the secondaries, but with a cutoff on occupation number. That's why they appear as secondaries. But it looks like what you say. Yeah.
So I could think of them as just acting perhaps in principle multiple times, but at some point it gets cut off.
Yes, exactly.
They cannot act infinitely many times like the primaries that have.
I don't know if every example is like that, but we have examples like that. Yeah.
Yeah, just had a small question on the example you showed. The reason that you set the 3x3 subdeterminants to 0 is that's because n is equal to 2 in that case. So
yes, that's right. That's right. So if you look at what M looks like in this case, oh, sorry, I was going the wrong way. So if you look at what M looks like in this case, if n is 2, this matrix can have at most a rank of n. So we took n as 2, the rank was 2, it was a 3x3 matrix, so its determinant must vanish. Yeah.
Any more questions? So Robert, why BF and matrix model? Why not BFSS?
So in BFSS, you're really meant to be dual to flat space. So any black hole that you have there will just Hawking evaporate to nothing. BMN is meant to be, you're still in something like this oscillated potential. So the black hole would be stable. It would radiate, but it would then reabsorb. So eventually it would come into equilibrium with its thermal atmosphere. So for BMN matrix model, you really could have a stable black hole, but not for BFSS. Yeah.
Okay, let's thank Robert again.
Completely new, and I think it has more necessary. People have more, if they're
The speaker would be Sam. Sam, and different problems. It's not really long about raising the sound.
Okay. Okay, thank you for that. Thanks to the organizers as well. So yes, I'll be talking today about two recent preprints with my master's student, Kaylee Mattison, back over there, and an old postdoc, Pratik Roy, who's now in Warsaw, and two postdocs, Advait and Tanay. Tanay actually also just left to Bariloche. Okay, so I'm gonna be a bit quick for two reasons. First of all, because SOC did some of the preparation already, and secondly, because I prepared way too much. So I hope you bear with me. So the goal is to study the nature of black hole microstates within the context of ADS-CFT. Now, historically, there's been a lot of progress with respect to black hole microstates, essentially always using concepts of ADS-free CFT2, in particular, the fact that the BTZ black hole entropy can be exactly related to the Cardy formula in CFT2. But I think it's fair to say that the actual microstates that we're counting there are far less understood. And the questions that arise is, what is the dual to a typical heavy CFT state? For example, does it have a horizon? Does it have a singularity? And you can also ask, what are the generic features of those states, if any, right? So the setting that I'll be working in is the four-dimensional setting, the NS4 SUN theory, at large but finite n, and strong coupling. So in that context, we expect that an ensemble of e to the SPH 1/16 BPS states would be describing what a BPS black hole in the bulk, which turns out to be a Kerr-Newman black hole. So the reason, of course, for focusing on the BPS sector is to have control at strong coupling. Okay, so recently, as SOC has reviewed, there's a sharp distinction was proposed in CFT language between perturbative supergravity states and black hole microstates by Chang and Lin. And the idea is that somehow graviton operators in the CFT, they will be BPS independent of n. So I can write down the form of an operator where the letters in the operator, the major C's, can grow in size. And gravitons then would be BPS for any value of n. Any graviton operator would be BPS. And that's why they call them monotone. Whereas non-gravitons, you might say, or these black hole microstates, they would be BPS for sufficiently small n, but fail to remain BPS as n increases. Okay, and that's why they are called fortuitous. And the mechanism here is precisely trace relations, and in particular the fact that the trace relations of a larger n theory are strictly included in the smaller n theory. So it could be that you are BPS by some trace relation that necessarily will disappear for sufficiently large n. So what is the rationale behind this proposal, at least as far as I understand it? Well, first of all, these monotones were sort of constructed and showed essentially to be in one-to-one correspondence with supergraviton multiplets on the ADS side. Okay, there are some recent slight doubts about that, but it's certainly true at large N. Secondly, so that means that whatever the black hole microstates are, they can't be monotone. Okay, but another perhaps slightly more intuitive reason is that if we work at some finite n and we look at the entropy of states for a given charge, and we fix that entropy, and as we take n large or g Newton to be small, then the area decreases of these states. The Bekenstein-Hawking entropy would decrease. The area would decrease, and the idea is then that somehow these states lift from the spectrum, and of course new states for larger values. So that would be the charge of the state, specifying this charge of the state. The charges to conserve charges. So the motivation for our work is to test this proposal, and to test the proposal, it should be clear that you just need to understand this BPS spectrum. You want to properly understand the BPS spectrum. So how do we proceed doing that? I'll be very quick, but we're going to look at BPS states. So those are certain representations of the superconformal algebra. So Sok explained many things of this. So for me, the important part is that a superconformal multiplet in the NS4 theory will be labeled by a conformal dimension, 2 angular momenta in R4, and 3 independent R charges. Now, how do we define the BPS states, or the short multiplets? Well, consider an anti-commutator between a supercharge and a superconformal charge. I'm going to make this specific choice here. That anti-commutator, because it's Q dagger, is bounded from below. It's positive semi-definite. And it can be written in terms of some combination of the charges. Now, generic multiplets of the algebra are long. That just means that each state in the multiplet has a Q or Q dagger partner. But what we call a short multiplet, or a BPS state, is those states which saturate this inequality. Because if you saturate this inequality, that's actually equivalent to being annihilated by these supercharges. And as Sok explained to us, so that is what we would call a BPS state. And by sort of a Hodge argument, these are actually equivalent, in one-to-one correspondence with Q cohomology classes, meaning states that are only annihilated by just the supercharge, not Q dagger, but modulo Q exact states. Okay? Okay, so now in the free theory, it's very easy to list all the BPS operators. So the NS4 theory has some field content. It has a vector multiplet and 3 chiral multiplets in an NS1 language. And then you can just check the charges and look at the components of the fields that saturate this inequality. You find that it's some component of the field strength, some gauginos, some components of the chiralinos, and scalars, so 3 scalars, 3 holomorphic scalars. And also 2 derivatives in 4 dimension have the right quantum numbers to be BPS. So then in the free theory, a 1/16 BPS operator would be a trace of a word formed out of these limits. Okay, and that's guaranteed to be BPS. Okay, but there's this issue that as you turn on the coupling, what can happen is that short multiplets can recombine into long multiplets. So some states may develop anomalous dimension and are not annihilated anymore by these Q and Q daggers. So there's a very non-trivial question, which is the question, which of these multiplets remain short at non-zero coupling? Okay, because we want to study the BPS spectrum at strong coupling for holographic purposes. Okay. So then there's an important conjecture, which is sometimes I think, I refer to it as the one-loop conjecture, which was actually made in Sok's paper, but he said he never conjectured it. he denies it. But anyway, so that is that the spectrum at one loop. So we only calculate anomalous dimensions of one loop. That whatever lifts as you go from the free theory to one loop, no states further lift after that, just that one loop effect. Okay, now this is actually turns out to be not quite true. There recently a counterexample was constructed that's in kind of a specific context. At present, I think it's fair to say that the status is a bit unclear. For SUN theories in particular, the status is unclear. We don't know of any counterexample for SUN, but they may well exist. Just all right. Anyway, for me, this won't be too important. I just wanted to explain a little bit how people who think about the BPS spectrum, how to construct the BPS spectrum at strong coupling. So we will use this conjecture, and we'll use this connection between BPS states and Q cohomologies to arrive at the statement that then the BPS spectrum at strong coupling would be at least in one-to-one correspondence with the tree-level Q cohomology. Okay. Now, using that idea, a very large class, if not all, that's that footnote that I just mentioned, all monotone operators have actually been constructed some time ago. And by that, I mean they're Q cohomology classes, tree-level Q cohomology classes. So then, okay, those monotones have been constructed, but we want to find the black hole microstates, which should be fortuitous. So how do you go about that? Well, the idea is to consider something called the superconformal index that I'll explain in a moment. So it's in more detail, but it's a partition function over the BPS spectrum that only gets contributions from the BPS spectrum, but it counts operators with signs, whether you're a fermion or a boson. And the great aspect of it, so that you might say that's a bit of a downside, a disadvantage that you're counting with signs because you're not really counting them. But the main advantage is that it's exactly calculable. And then the idea is to look. So we know what the monotones are. We can calculate the full superconformal index. We can then look at discrepancies between the two indices to get some ideas about where these fortuitous operators are hiding. It's not perfect because you're not really counting, but it gives you some idea. Okay, so the point here is that the superconformal index is an important quantity. So it counts these BPS states within quotation marks or short representations, and it's some mathematical expression that looks like this. So you take a trace over the full space of states of the theory. You weigh it with various charges, and you include this -1 to the f, which is responsible for counting bosonic and fermionic states with opposite signs. Now, there's the usual argument. This trace is designed in such a way that long multiplets of the superconformal algebra, they cancel in this trace, and that means that the index will be invariant under recombinations. So that means that it's topological or protected. So we can compute it in the free theory, but are guaranteed that that expression will also give the correct expansion even at strong. So there's a very explicit formula for the index, therefore, because you can calculate it in the free theory, where we just can write it down exactly. I won't go into the details, but it's some integral over something over an integrand. So what is the integrand? The integrand, you forget about gauge invariance. You just write down all BPS operators, all matrix degrees of freedom, and you multi-particle them. You build the Fock space out of all these matrices, their derivatives, and then you worry about gauge invariance after. So you use this integration to project onto gauge singlets. Okay, and that integration is integrating over the gauge group with the invariant Haar measure, and that can be expressed as an integral over the eigenvalues of the SUN matrix. Now, okay, so this is an exact form for the index, but I want to say that its explicit form, of course, really only manifests the free BPS spectrum, modulo trace relations. Okay? Okay. So now these integrals, most of the time, these integrals have sort of been evaluated only to finite order. Okay? And then you can do this check of comparing with the monotone index and finding discrepancies. But I want to ask the question, can we find closed form expressions for the index which do not manifest the free BPS spectrum, but rather reflect, at least encodes some features of the BPS spectrum at non-zero? Okay, so maybe schematically, I've given you an expression that looks like a trace over the space of states at zero coupling. Can I find an expression that I can interpret as a trace over the space of states at non-zero coupling? Okay, that's the questions. And in the remainder, I will argue that at least sometimes, in some cases, this can be. Okay, so I'm going to look at free kinematic limits in increasing order of complexity. So there were these fugacities, P and Q, they couple to some of the charges. And I want to first take P and Q to zero. That gives me the simplest possible index I can define, which is known as the Hall-Littlewood index, which captures quarter BPS states. Then I want to go to the McDonald, or sometimes called the Schur sector, which captures 1/8 BPS states. And then finally, we'll briefly talk about the 1/16 BPS states. Now, I should say that in these first two cases, no fortuitous classes are present, or at least the expectations that they are not there. But the method of evaluating these indices or these integrals, that will generalize also to the 1/16 BPS. So it's a good warm-up case. Yeah.
Maybe I missed something. So you're saying that some BPS states at zero coupling, they stop becoming BPS one loop, right?
Yes.
The index, I guess, does not change, right?
The index doesn't change. The index
going up in pair.
The index is designed such that long multiplets cancel.
Yeah, but now, so what do you want to reformulate to capture that information? Maybe that's what I missed. Now you want to say you want to rewrite the index?
Yeah.
Which does not know about this in a way that it knows about it.
It
can kind of guide you which BPS states.
Well, the index is this. The index is the same for the free space of states and the space of states at weak coupling. Let's say, right? So the question is: so in some sense, this expression in terms this expression contains many superfluous states, many contributions that may lift. So the question is there a nice form? Can I write the index in a form that doesn't contain all this superfluous information, but rather contains a bit less? It's a more minimal expression. That's what I'm doing.
More minimal, but does it map to these sort of BPS contributions that lift versus don't lift?
But the ones that lift you'll never see, right? Because they cancel. So it's the guys that remain, but then really the differences of the guys that remain. But it's
So instead of counting everything, but you know that some of these are not there at one loop, you want to count only the ones that remain. The answer is going to be the same.
I want to see if there's a more minimal expression that reflects just stuff that remains.
It's about the calculation, not the final answer, because the final answer is not going to change, right, of the index.
Yeah, but the expression can change, right? It can be, yeah. But if you would expand it, you wouldn't see the difference. But I want some closed form that from which I can read off maybe some aspects of the spectrum. Okay, so let's start with the very simplest case, the SU2 Hall-Littlewood index. That's very simple. There are only 3 letters that contribute to scalar matrices, one fermionic matrix. I can write down that expression that I gave you, specialized to this case. So this is the expression. So this really corresponds to the X letter, the contribution of a bosonic matrix, another bosonic matrix, and then the minus XY reflects the index of the fermionic matrix, which comes with a minus sign because of minus the F. And then, okay, all these fields are valued in the adjoint representation, and I project onto gauge singlets. Now, using this integral, you can convert it to an integral over eigenvalues for SU2. There's just a single eigenvalue. So this actually becomes a contour integral over the SU2 eigenvalue, which is just a face. So it's a contour integral over the unit circle. And I can evaluate that by residues. In this case, that's a very simple integral to do. The pole structure is very simple. There are free poles. I pick up the residues. And after a simplification of the residue sum, I find the following expression. So, okay, so what is the interpretation of this object? Well, the denominators, and this is a bit similar to what Robert was talking about, how the Hilbert series look for Robert. So there are two bosonic, gauge invariant bosonic generators, trace x squared, trace y squared. Those are acting freely. They're like primary invariants, and they appear in the denominator. There are two fermionic, gauge invariant fermionic single trace operators. Those appear with a minus sign in the numerator. There's only one fermionic eigenvalue here, so they only can appear once. Then finally, you might be a little bit puzzled about this trace xy, because it's a bosonic single trace operator, but it appears in the numerator. It appears as a secondary. So what's going on there? Well, this weird appearance, if you want, of trace xy is actually related to the absence of one single trace operator that would have contributed in principle, which is trace xy psi z. But it turns out that actually the square of trace xy, or that linear combination in any case, is a Q-exact operator. So actually, you can think of this is an example of the lifting phenomenon, where a double trace operator lifts, forms a long multiplet together with this xy psi z. They lift from the spectrum. They're not seen in the index. So I should only consider a single power of this trace xy. And that's why it appears in the numerator. Now, the upshot of this expression is that I've listed all the generators. I've interpreted in terms of gauge invariant operators. And it turns out that all these guys are monotone. Okay, they are annihilated by Q for any value of n. They don't depend on trace relations. So indeed, that's sort of consistent with the expectation. There's no fortuitous operators in this set. Okay. Okay, so that was very simple. Maybe I should just briefly pause if there's any questions.
So Sam, what are the Q transformations? Q on X is 1.
Q on X and Y is 0, and Q on psi is a commutator of X and Y. So that's how it's related by trace relations. That object then becomes this difference, SU2 trace relations. Okay, so we want to do something a little bit more complicated. So we want to look at this McDonald index, or 1/8 PPS sectors. In this case, the letters that contribute in the free theory are again x, y, and psi z. So those are the same as in the Holder-Toowood case. But now we also have a component of the gaugino, and we have an infinite set of derivatives. Okay? So you get a slightly more complicated, well, considerably more complicated integral, because as you can see here, these are actually now infinite products, okay, in the denominator. So there's an infinite amount of poles now. Yeah, and that is due to the infinite amount of derivatives. So for each derivative, I have an oscillator, a bosonic oscillator. Those contribute those denominators. So can we evaluate this by 5 more minutes? Can we evaluate this by residues? Well, integrals of this type are actually quite well known in the mathematical literature. They're known as basic hypergeometric integrals. And so the general basic hypergeometric integral discussed in classic textbooks looks something like this. Okay. Now, we can easily look at the denominator there and just list the poles inside the unit circle that we have to try and pick up. So they appear at any s equal to any di. Here, di's I assume to be smaller than 1. So they appear at any di and then multiplied by an arbitrary positive power of q. Okay. So I've sort of illustrated it there. So you have sort of different annuluses in the complex S-plane. And for each annulus, we'll have a pole where the annuli are separated by the absolute value of q. Okay, now that's fine. So there's lots of simple poles here. But there's one issue. Turns out to be there's an accumulation point of poles at the origin, resulting from the infinite towers of poles. And there's also the integrand also has an essential singularity. There you get something that is called an unisolated essential singularity, which is about as bad as it sounds. So it's not that obvious here how to use Cauchy's theory, how to evaluate this by residues. Okay, but these mathematicians, of course, have studied this. And it turns out that you can show, modulo some conditions, you can show that the residue at the kth annulus will contribute at order zeta to the k to the series where zeta is this number determined by the ratio of parameters that multiply S inverse. That's not too difficult to show. And in particular, this means that the residue sum will converge as long as this absolute value of zeta is less than 1. And actually, what you can argue using the convergence of that residue sum is actually that then the contribution from this nasty singularity at the origin will actually vanish. So convergence of the residue sum is closely tied to actually that you not have to worry about this essential singularity. But of course, we are in trouble because, of course, our integrand is precisely such that the zeta is 1. That means that the residue sum will diverge, and that sort of means that I can't argue that the origin contribution vanishes. And these things are tied together. So somehow this weird thing that happens at the origins should somehow cure the divergence of the residue sum, but I can't make sense of it using Cauchy's theorem, and I'm sort of left. Can't do anything anymore. Now, what we found is that this issue can be resolved by changing the integrand slightly while not changing the integral. So it turns out that this integrand has a symmetry, a residual gauge symmetry, if you want, which is the Weil symmetry of SU2, which is in this case Z2, and you can fix that symmetry. And when you fix that symmetry, you can show that the zeta takes on a value that has absolute value less than 1, and that means the residue sum converges, and the contribution from the origin vanishes. And that generalizes to higher rank gauge groups as well. So that is I would say, a new method of evaluating these integrands with an infinite amount of poles as a residue sum, just using Cauchy's theorem. Yeah. I'm going to skip the details there because I'm almost out of time, I think. So let me just flash you then the results. So you get this expression. Okay, it looks a bit complicated. It is. I'm not going to say probably too much about it. I'm just going to say that for a specialization of the parameters, you can show that this series on the right actually simplifies, and we get a product formula for the McDonald index. And that product formula can be interpreted very similarly to the whole Littlewood index, but now in terms of an infinite set of single trace operators, because we have an infinite set of derivatives. There's a relation there. Now, this expression again suggests that the McDonald index, at least this specialization, can be fully accounted for by monotone operators. And this is kind of what I was after. I wanted to have some closed form that can be naturally interpreted in terms of operators that remain BPS. So this is an example, is a more non-trivial example of that motivation that I explained in the beginning. How much do I have? Another maybe 5 minutes? Yeah. Because I just wanted to just briefly, I think I started a bit after. Yeah, okay. So I just want to touch on, so this was the context of one paper, of the earlier paper. This method also works for the full index, the full 1/16th BPS index. We can calculate the residue sum, can show that it converges, that it's all fine, but we can't really simplify it in a way yet that exhibits the strongly coupled spectrum. So evaluating the residue sum is not quite the same as getting it into a form that reflects encodes these features of the spectrum. You need to do this additional step of simplification, and for this guy, it's just so far too complicated. Now, I just want to very briefly touch on the second paper that we've written, where we try to, we've found some nice expressions, but they all involve just a purely monotone spectrum. So what can we also do something for the fortuitous spectrum? And for that, we can actually make some progress, but you have to use what is called a one-loop index. So it turns out that at one loop, there's actually the NS4 spectrum, the PPS spectrum, admits one additional symmetry called the U1Y bonus symmetry. And this symmetry is the charge for this symmetry is that the number of letters in an operator is preserved at one loop, under the one loop Hamiltonian. You can use this symmetry to define a refinement of the index, where now we have sort of 5 variables as opposed to 4. This reduces to the ordinary index when I specialize this 5th parameter z. And now this index, it's still an index, but it's only an index going from free to the one loop spectrum. Okay, I can't really go beyond that, but okay, I can at least write down an index that is protected from free to one loop. You know, assuming the one loop conjecture, that's doing pretty well still. Okay. So with this refinement, we have more limits, more kinematic limits that we can take if you want. And now we can again take this P and Q to 0 limits, where the integrand reduces to a rational function, and we're quite good, but we have many more letters contributing. We have X, Y, Z, we have free scalars, free fermions, and also the field strength. So this sector, this index was introduced by Sok and his collaborators, and it captures some part of the 1/16th BPS sector. Okay. And so in this case, closed form expressions for the full index are easily obtained because it's just the residue integral of a rational function. But we want to do a bit better. We want to subtract the monotone index as well to really get an idea of what the fortuitous index is and about the fortuitous spectrum. And it turns out that actually this monotone index is somewhat more difficult. It's much more difficult to evaluate, as it turns out. And we've made a little bit of progress there. So I think I should finalize, but the key idea that we've used is that some of these monotone operators, they transform in representations of an SU-free subgroup of the R symmetry. And we decided to focus on singlets under this symmetry. And there it turns out that the spectrum simplifies considerably. And let me just flash you the expressions that we find. So we find that in these cases, the monotone index for SU2 completely trivializes. So there are no monotone SU-free R singlet operators. They're just not there. We've done this, we found this by explicit construction. Similarly for SU3, n equals to 4, there are some singlet monotones, but they're actually truncated. There's only two non-trivial monotone operators. So in these cases, we get a very simple expression for the monotone index. We can also calculate the full index in this singlet sector by doing an additional projection. Now, do a similar projection as the gauge projection of the index, but now an additional SU3R projection. And then finally, what we find is this formula for the fortuitous index for the SU2 theory in closed form. Okay, so this is all there is to it, at least when we look at these R symmetry singlets. And from this, you can indeed deduce some structural features of the fortuitous spectrum. I'm going to leave that. If you want to learn more, you can come to me after the talk. We can similarly evaluate a closed form for the SU3 case. And again, this suggests some features of how these fortuitous operators also in the NS4 SU3 case are organized. Okay? And hopefully will help also Suk and his collaborators to construct explicit examples of these Q combinations. So let me leave it there. Thank you.
Questions? Any questions?
You use the word strongly coupled a few times. By that, did you mean one loop, or did you mean something?
Sorry, yeah. Well, yeah. So so the index is, I don't know in which context I was saying it, but the index itself is true, is correct even with strong coupling.
But I guess what I'm wondering about is if it keeps, if the spectrum keeps changing at every loop order, right? Is it? I mean, do you need now to keep adjust, like, you know, you might have to do another, because you said that 2 loops, maybe some 1 loop states stop being BPS, right?
Yeah.
And maybe that keeps going, right?
But it's not,
So it's an indication of what the actual states. I mean,
so it was for the longest time, it was believed that after everything that can lift will lift at 1 loop. Yeah. Recently, a counterexample to that. I think even that counterexample, there is some confusions. At least I personally have some confusion about these counterexamples for a very specific gauge group. But yeah, I think the status is just unclear. We need more examples. People need to find examples, but it could also be true that the 1 loop conjecture holds for SUN. So it's just not clear. Yeah, it's just not clear. In that case, what I say in principle can be transported to strong.
Any more questions?
So each residue in your residue expansion is a Higgs fraction, right?
Sorry?
Each residue in your residue expansion is
Yeah.
Higgs fraction, right? You give some expectation values to some operator after making it happen.
Yeah. So,
That is what you have identifying the residue expansion. With the black hole point.
yeah. So you're saying if I look at individual towers of residues, whether that, yeah, there are some examples where such an interpretation has been made, but as far as I am aware, this has never been done for the NS4 here. So this has been done for some NS1 gauge theories with sufficient fundamental matter, because you need a Higgs branch. There's a Higgs branch.
Each pole is a location of a condensation of operators. You pull the temper carefully to make so close to pole.
Yeah.
Corresponding operator becomes massless and you think it bad.
Yes.
The residue is Higgs branch infrared in there.
Yeah.
I'm just wondering if that interpretation helps possible identity.
I've not thought. I know what you're referring to. I've not thought about it carefully enough. So I can't really give an answer. I hope that something like that could exist. Yes, that would be very useful, especially for the full index, because in that case we kind of need to work with the individual residue at the moment, because I don't have a way of massaging it into a form like the McDonald or how little it means. So if there is an interpretation to one of these terms itself, that would be very great. Yeah, I don't know. Yeah. Yeah. So okay, sorry. So this is in the SU2 theory. This is the expression for the index of fortuitous operators. And what was well known is that at order 24, let's say, is roughly a count of the energy. What is called a threshold cohomology appears, just meaning it's the first fortuitous cohomology that was found. And let's call that guy O0. Okay. Now the next one appears at order 30. At least in the singlet sector, and that's quite easy to understand, because you can calculate, you can get to a superconformal descendant of the threshold cohomology acting by free Qs, and free Qs is again this SU3R singlet. So it's just a singlet superconformal descendant of the threshold cohomology. And these Qs act in such a way that each Q adds 2 to the power of T. But in the SU3 case, you see there's again a threshold cohomology at order 24. But now the first power of T only appears 18 steps later. So that can't be explained in terms of a superconformal descendant. So you might ask, why is there no superconformal descendant of this guy appear? It could be that it cancels against something else and the index doesn't see it, right? But it's at least, I mean, some interesting.
Check why
No, we haven't yet. But it's something that we want to do. In fact, there's some puzzle. I think that there was some, even about this order 24 term, there was some puzzle about the fact that for SU3, the threshold cohomology appears at the same power as for SU2 was also a bit surprising, I think. So maybe there's something off about this guy. Maybe it's an example of something that could lift at higher loop. It's not entirely clear. Yeah, SU4 we did as well. So I haven't written it because we haven't completed the calculation. But when you include when you do these calculations for SU4, so the monotone index sort of gets more complicated. So SU2, SU3, it truncates at finite order. For SU4, it turns out that there is a singlet monotone that you can write down that is bosonic. So you get an infinite tower. It's still very sparse, very simple, because you can resum it. But yeah, we haven't fully completed that calculation. But so it does seem somehow that this SU3R projection, it really simplifies the monotone sector. So somehow the monotone sector is very sparse in terms of these SU3R singlets, whereas you keep lots of interesting fortuitous operators. That's kind of the luck, at least so far luck that we're having in this singlet sector. But of course, we'd like to better understand why that is. Yeah.
Is there any more questions? First slide, I see that T forward. No. Previous slide. You showed a long power sharing with PG.
Oh, yeah.
Yeah, I see that T power 48 is missing. Isn't that a bit strange?
I mean, yeah, we don't really know at this stage, but it could be that there's just a cancellation because it's an index.
Because from 80 to 90, it's always 6. You're adding
Yeah, no, so yeah, these steps of 6 are kind of.
They are all steps of 6.
Yeah, no, yeah, it could. Yeah, it could just be an accident that at that stage you both have a bosonic and a fermionic operator. Index indices differences. Yeah, we would like to construct the actual cohomologies. Of course, this is really only the first step. But this is getting some ideas about how the spectrum of these fortuitous guys is structured in this sector. The next step is to actually construct the operators.
Okay, let's thank again.
thought is, Jello is going to continue on holography to extent MITP.
Okay. So welcome back. So I think my lecture from last time probably got a bit technical towards the end. So let me help you remind what are the main things to remember. I mean, it's totally okay that you don't remember the details. You are not need them. So what I talked about last time, what I was trying to last time basically was how to compute Feynman diagrams in ADS. These are called Wilson diagrams. And we looked at 4-point functions, and there's two types of diagrams. One is called exchange, the other one is called contact. So the main message from last time was basically these contact diagrams. You can evaluate them in closed form in terms of functions like me2. And these exchange diagrams, you can write that as the final sum of these contact diagrams. Of course, there's some conditions or something like that, but these conditions will be satisfied in what I'm going to talk about today. So these Witten diagrams, they form the building blocks for doing computational theory in EDF. So let me very quickly review how people used to do this. So the procedure is actually similar to class-based. So the first step is to start by writing down all the rules, right? So for that, you basically want to get all the vertices from some effective Lagrangian. And here we are focusing on tree-level 4-point correlators. So that means you need all the cubic and quartic vertices. So this is the cubic vertex, and this is the quartic vertex. So this is step number 1. The step number 2 is to write on all the diagrams. Well, to enumerate all the diagrams. And the last step is to compute these diagrams and add them up. So this may look like a very straightforward procedure, but in reality, it's actually very complicated. So the reason has to do with the fact that we have infinite many particles I mentioned last time. So let me remind you. So here we are focusing on the theory of 4-dimensional n for nuclear mills, and this is due to be string theory on ADS vertex 5, but we are looking at the large n and the large tau coupling limit. So this is basically the gravity on ADS 5. So the Tandy theory is actually not that complicated. Basically, just have one like superfield. But when you put this on ADS 5 times S5 and then further perform a KK reduction, you will get infinite many particles. The reason, well, so what is this KK reduction? This basically you are doing like some separation of variables, right? So you want to separate your field to an ADS part and an S5 part. So on this S5 part, you will have all kinds of angular momentum. Or more precisely, these are representation of the isometry of SO5. This is also sometimes is often called the R symmetry. And the spectrum on this S5 doesn't have any upper bound, so you have, well, I mean, there will be some upper bound because of the string exclusion principle, but for this n goes to infinity limit, it's like infinite, you have all these different particles. So that will lead to infinite particles. And from the field theory perspective, it's also easier to see why you have infinite particles. It's because you have these operators. Let me label them by K. They carry K indices. So basically, you have a product of these scalars in n equals 4 superior. So basically, each I goes from 1 to 6. These are 6 scalars over n equals 4. And they are in the symmetric traceless representation. So when you include more of these x's, you have a longer operator, and the dimension equals to the number of fields you have here. So these operators, they are due to these particles in ADS. And as you can imagine, the interactions among these particles, they are extremely complicated. So in fact, people tried to write down the most general vertices you need for computing an arbitrary 4-point function, where these operators can, have length k1, k2, k3, k4. And they found just to write down these rules, you need 14 pages. So although this is a sort of a straightforward procedure, and we know how to compute individual diagrams, in practice, it's very complicated to carry out because of complicated interactions. And moreover, as you increase size of the external operators, there are more and more operators which can appear in the exchange. So you will have more and more diagrams to evaluate. So this is something that works in principle, but in practice, like before 2016, there were only like a handful of examples which were computed in this honest way. So today I'm going to show you a different strategy to compute these correlation functions by using the philosophy of bootstrap, and we will see that how we can get all these correlators without working too much. Now, okay, so I will actually present 2 ways to do this bootstrap calculation. But before that, let me first say a bit more about the kinematics of these 4-point functions. So these are the operators we are going to focus on. As I mentioned, these operators, they have dimension delta equals to k, and they are in the rank k symmetric traceless representation of SO6. Or if you want to label them using the thinking labels of SU4, so they're 0, k0, okay? Now, because the asymmetric quantum number matches the conformal dimension, so these are protected operators. They don't receive quantum corrections to their enormous to their conformal dimensions. And I will also call these operators super gravitons because these are scalar operators. So L equals to 0 for these guys. The real gravitons, they carry spin. So I want to use the word super to distinguish from the spinning ones. Good. Now, one thing you'll notice here is that these operators, they carry many indices. They carry k indices, and it's a bit annoying to work with so many indices. A nice trick to keep track of the asymmetry information is to contract these indices with some auxiliary null vectors. So what I meant is you can define an operator without indices by contracting this operator dependent on x with some 6-dimensional vectors. And here, each vector in the product of itself is 0. So what this does is that it guarantees whatever you are multiplying with this k index, this string of indices will be automatically symmetric. So this is clear, right? Because these t's they're bosonic. So this already makes this a symmetric combination. And moreover, this null property ensures that the traceless nature of this OK. Okay, so that's just a trick, and you can view this X as the space-time coordinates for like the boundary of ADS. And this you can view it as some sort of coordinate on the internal S5. Okay. And the thing we are interested in computing are 4-point correlators. Sorry, I'm switching. Let me still call them K. K1 to K4, which are functions of X and T. So this is just the 4-point correlator. Okay. Now, because we want to use the bootstrap strategy to compute these guys, so we should try to understand better the constraints from symmetry. Yes.
It's a primary key complex.
Huh?
It's a primary key complex.
Yes.
Because
exactly. Yeah, it needs to be complex.
Yeah.
They transform as a vector on the SO6, but it doesn't need to be real.
And how can you use TS visualizing S5?
On S5.
Just because they have information on this.
Right. So this will automatically make this symmetric traceless, right? So I mean, whatever's multiplying this will be projected to the symmetric traceless representation.
But that P itself is parameterizing S5 in some way. It's not that.
Loosely speaking, yes, but yeah. Otherwise, you need like t squared equals to 1.
6 parameter subject to 1 constraint, so
right.
Complex 5, right?
Yes.
Complex 5.
Yes. I mean, this is like, just think of it as some polarization vector to keep track of the polarization in the internal direction. Yeah. That's probably the more precise answer. Yes.
Is it possible to have a complexified Wilson loop using scalars and the gauge field?
What's the loop?
Yeah, where this vector T can be used to construct that.
Yeah, I think so.
There is such a construction, right? There is something called Mandelstam and loop.
Yes.
Related to this, or is this the same T, or?
It's the same T.
Because there also, I think there is a null one when we introduce scalars into the gauge field.
Yeah, it could be. I mean, this is just basically a very easy trick, like to make things symmetric traceless. Doesn't really depend on which setup you're considering. Yeah. Okay, so now let's try to understand what symmetry means for these subjects. So one thing you can do, as for example mentioned in Kosti's lectures, that you can extract some kinematic factor. Basically some combinations and products of 2-point functions, so that your correlation function can be written as a function of cross ratios. So here I'm using the curly G to denote functions which are functions of cross ratios. So this is already like you're already reducing the number of variables, right? So previously you have all these X and T's, but now you only have 4 cross ratios, which I'm going to define more precisely. So this U here is the same U introduced by Kostis. So this is basically just some ratio of xij like this. And v is similar with a different numerator. And as in these lectures, so it's convenient to introduce the parameterization where you write this as z and z bar. So the physical meaning of this z and z bar is essentially you can use conformal transformation to move these to fix three of the operators to be at 0, 1, and infinity. And then there's the one which you cannot fix and has complex coordinate z and z bar. So you can basically put all of them on a two-dimensional plane. And similar to U and V, we also have these R-symmetry cross ratios, which are defined as T13, T24 divided by T12, T34. And there's also tau. So they are analogs to U and V. So here, Xij is Xi minus Xj, but Tij, I define it to be Ti dot Tj, okay? And similar to this, the ZZ bar coordinates, I can do a change of variable to write them as alpha and alpha bar. Okay, so these are the conformal cross ratio. This is the R-symmetry cross ratio. So by writing your correlation function like this, you have individually used conformal symmetry and R-symmetry. So let me remind you, R-symmetry is the isometry on this file.
Excuse me, are sigma and tau real? Yeah. Because you wrote in terms of alpha and alpha bar, which
doesn't matter. I mean, they're complex.
Alpha is not conjugate.
No, they're independent.
Okay.
Yeah, they're independent.
Thank you.
Yeah, thanks for the question. So, if you look at this, so these are just they're bosonic symmetries, right? But our theory for the N equals 4 supersymmetry had a much bigger symmetry, which is N equals 4 supersymmetry. Superconformal symmetry. Superconformal symmetry. So in particular, this also includes fermionic generators. Right? Like these Qs and S. So the invariants with respect to these fermionic symmetries, they will impose further constraints on this function G of UV and sigma tau. So it's a bit of a technical thing, which we don't need to care about how it's derived, but let me just state the result. The superconformal symmetry as the fermionic generators, they impose further constraints known as the superconformal word identity, which basically just relates UV and sigma tau. So it has a simple form that if you act on your 4-point function with such a differential operator, and then you restrict yourself to the slice where alpha equals to 1 over z, then you get 0. So on this slice, you can see the DD bar dependence and alpha bar dependence, they're related. So this you can derive in many ways. It also has something to do with this so-called Taylor algebra construction. But let's not go into details. So here I've written down only one identity. Actually, you can get more by interchanging z and z bar and alpha bar. And the reason is because here you can see this z bar in exchange is just a redundancy in the parameterization when I go from UV to z bar, and similarly for alpha and alpha bar. So in total, I have 4 constraints. And these 4 identities, you can easily solve them. And the answer takes the following nice form. So you can write in a 4-point function as the sum of 2 parts. So this is known in the literature as partial renormalization theorem. So here, the 4-point function includes a free part. This for later. This is the value of the 4-point function at 0 coupling. And then there is the part which depends on coupling, which I will call it the reduced correlator. And there is a factor R multiplying this reduced correlator, which is completely determined by conformal symmetry. And it can be written in terms of cross ratios as the product of 4 terms. Okay, so this is basically what we can extract from superconformal symmetry. Constrains the form of the 4-point function to obey these identities, and the solution to these identities takes such a form. Are there any questions at this point? Good. Now, just with this, we cannot we cannot really write down the correlator because these constraints are valid for any coupling, right? So the free theory will also obey that with h equals to 0, right? So in order to make more progress, we need to input a little bit of information. In particular, we need to make the problem aware that we are, for example, looking at the supergravity limit. So how do we do that? So I'm going to introduce 2 different ways to do that. One way is more how should I say, it's more elementary, and it's not as streamlined as the second one, but it will be a sort of proof of principle to tell you that symmetry and consistency conditions are indeed enough to fix the correlators. So let me start with that. So I will call this the sort of the position space approach. So the position space approach is actually very similar to the traditional way of computing correlators. But the major difference is that we do not want these 14 pages of indices as an input. So what we want to do is that we want to write down an ansatz without inputting the vertices, but then we fix this ansatz by supersymmetry. So let me explain a bit more in detail how this works. So we start with an ansatz. So the ansatz for the 4-point function has the form which is expected from the sort of Witten diagram approach. So you know it will be a linear combination of all the possible Witten diagrams. And in particular for this exchange Witten diagram, so that's the thing we discussed last time. So you can exchange not only scalars, but also fields with spins. I'm labeling the fields with X. And so this is sort of like the ODS exchange. But as I mentioned earlier, like all these fields, they carry some asymmetry representation, right? So this is the information, the quantum number in the internal manifold. But when you exchange a field, you also exchange the asymmetry representation as well. So, so there will also be some function capturing the exchange of it's sort of like the S5 counterpart of this Witten diagram, right? So this will be, you can think of it as S5 exchange. And this is actually much simpler than the Witten diagram. This is just a polynomial in terms of the asymmetry cross ratio. Now the tricky part is about its contribution. which in principle, we know from if we know the vertices. I know we do the computation very precisely, but we do not want to do such hardcore computation. So let's just leave them as an unfixed number, lambda of x. So this is in the S channel. And you also should add the T and the U channels, which are related by crossing symmetry. And then you also have contact part. It's contact interactions, which are given by the quartic vertices. And here, just like here, we are going to parameterize these contact within diagrams with some unknowns, and we call them collectively call them mu. So here, we are going to include all the possible asymmetry structure, which in more precise terms is all the allowed monomials in terms of the asymmetry cross ratio. So I should have said like the dependent on sigma tau, the asymmetry cross ratios is sort of has only finite many structures. Has to do with the fact only finite many irreducible repetitions can appear in the tensor product of 12 external irreps. So the number is the same. So dependence on sigma tau is just a polynomial. It's very simple. And for these contact terms, we are going to make the assumption that at this quartic vertex, we have at most two derivatives. And this has to do with the fact in flat space, we know that supergravity without string equations is a two-derivative theory. So the vertices should not have more than two derivatives. So basically, for each diagram you can write down with the at most two derivatives, you multiply with the arbitrary asymmetry polynomial. So that's the outlet for the contact part. Okay. Now another thing I should say is that here, just X, what kind of fields X can we exchange? So this is actually determined by selection rules. And this contains two parts. One is R-symmetry selection rule, right? Basically tells you, 0K1, 0, that's the one operator times another 0K2, 0. There's only finite many repetition can show up. And because we are in a supersymmetric theory where these exchanged particles, they are in some short multiplets. So there's the correspondence between the KK level and the repetition. So this already guarantees that for a specific state of K1, K2, K3, K4, there are only finite many fields that can show up in the exchange. So it's not some infinite ansatz, this is already a finite ansatz. And there's another more sort of technical constraint, which tells you that whatever X can be exchanged, you need to satisfy this inequality that, delta 1 plus delta 2 minus delta X minus LX needs to be greater than 0. So if it is equal to 0, this is something called extremo. I will not go into details explaining that, but it's some sort of consistency condition imposed by the in the supergravity limit. So anyway, so what I want to convey here is like just from these simple rules, you can figure out what kind of fields you can exchange here. So the only unknowns are just these lambdas and these mu's here. Okay. So this is step number 1. Now, the second step is to evaluate the ansatz. And that's actually already covered in last lecture, right? Because these contact Witten diagrams, they can be obtained from the simplest D111, which is only 2, right? And then you can act with this way-shifting differential operators to reach the contact diagram you want. On the other hand, all these exchange diagrams can be written in terms of these contact diagrams. So what you will get for this ansatz is that it's going to basically be a linear combination of these Me2s and the lower weight, just logs. So basically, I can write it down in this form that it's sum can be expanded in terms of the D111, log U, log V, and 1, with some coefficients which are rational functions of the cross ratios. So here actually I skipped a step. So if you go back to last time's lecture, you'll find that so this is what I call phi, and you use these differential recursion relations, you find when you take a derivative, what you will get is the phi can always be written as phi itself, and log U, log V, and 1, and then you keep going, right? So that will convince you that the whole thing can be expanded in terms of just these things with rational coefficient functions. Okay, now comes the third step. The third step is that we want to impose reciprocal symmetry. And that's where the magic happens. So here we want to impose these identities. And after the action of this differential operator, you can easily convince yourself the ansatz can still be written as a combination of these spaces. And then you set the R-symmetry cross ratio to be 1/V. And you require this thing to vanish. And the condition for it to vanish is that all these coefficient functions, they have to vanish, because apparently the two cannot mix with just the logs, right? And the condition that, so let me call this R tilde, because I've already acted with some differential operator. So well, requiring these coefficient functions to vanish is actually simple to implement because these coefficient functions are rational functions of the cross ratios. So in Mathematica, you can basically just do together, right, to have a common denominator. And then you require the numerator to vanish. And the numerator is linear in terms of these unknown coefficients you have put into the ansatz. So this condition, what it gives you is a linear equations for these parameters. And then it's straightforward to solve them, right? You just require impose this linear significance and then you solve for these unknowns. And turns out very nicely, all these coefficients can be fixed from this condition. So what is the lesson we have learned from this calculation here? So the lesson is that we do not need to start with the explicit Lagrangian with all the details about the vertices. We just need to impose some very general properties such as supersymmetry and the fact that in the exchange we only have these PPS operators and their descendants, and it's sufficient to fix entirely the correlation function without knowing these vertices. So the bootstrap strategy, this is just to show the bootstrap strategy works for these angles, for this angles for the polynomial theory. Any questions? So how much time do I have, I think?
Full 24 minutes.
Okay. Now this is just like proof of principle tells you that symmetry is enough to fix the correlator, but apparently it's a bit still a bit cumbersome because you need to actually compute these Witten diagrams, right? And then you need to compute these answers and implement reciprocal form of symmetry to solve these linear equations. So you can do this like for some low-lying values of ki, but if you want to get the most general 4-point function, this is apparently not the way to go. So now let me tell you, there's a smarter way to do that in the so-called mailing space. I should first say a few words about what is mailing space. So mailing space, you can view it as some sort of ADS momentum space. It's in quotation marks because as we learned from Tarek's lecture, just as in DS, there's no translation symmetry in ADS. So there isn't really momentum, conserved momentum. But the isometry includes dilatation, which motivates us to use the so-called mailing transform.
Sorry, Shinan, just before we continue, so these amplitudes that you calculated now, just using superconformal symmetry, where should those be valid? Is this only at large Toft coupling? I mean, these only at large Toft coupling?
At infinite Toft coupling.
Infinite Toft coupling and large N.
And large N, yes.
I see.
Yeah.
So these would be some strong coupling predictions for some CFT correlators, large N correlators.
Exactly. So yeah, it's N equals 4 supermills at infinite large N and infinite Toft coupling.
So this would be the first term in a large coupling expansion.
I mean, the leading one would be just the 2-point function times 2-point function. So this is the leading non-trivial one.
Okay, I see. Leading.
Yeah. Right. So we do a 1/n expansion, and then we set lambda to infinity.
And are there methods to systematically correct this?
In 1/n or 1/lambda?
1/lambda.
Yes. So so there are different approaches. So one is to also you write down simple ansatz. These arise as like higher derivative equations, and then you can fix their coefficients by either using the flat space limit together with some localization result, or you can do it like by assuming there's an underlying Walshy description like Fernando and friends are doing, and that actually can make you go a bit further. So that gives you the 1/r correction. So the leading one would be the sort of Shapiro amplitude. Then you have this 1/r correction to that. Yeah.
I see. So you still bootstrap the
Yeah.
next order.
Because here, actually, for like string equations, it's impossible to do like an honest calculation because nobody knows how to do it. But you can get them from consistency conditions.
Okay.
Thanks for the question. Okay, good. So let me introduce this mailing space. So we are going to use the mailing transform, but in the end, the transform, the correlator, will have properties which look like flat space, momentum space. So let me first write down the definition. So basically, so the left-hand side is a function of xij squared, right? And here on the right-hand side, xij only shows up in this factor here. And this gamma function, you can understand as sort of a convenient convention. And then all the information is transferred to this function m, which is called veiling amplitude. Now, let's try to understand why it's appropriate to call this an amplitude. So it has to do with the following. So here, I first also need to tell you what this integral means. So the integral is not over all the delta ij, because we know on the left-hand side we have a conformal correlator. And these delta ij's, they must satisfy certain constraints so that the right-hand side is also conformal. And this integral is with respect to the independent delta ij's along the imaginary axis. That's what makes it it's really inverse Manning transform. So what are these constraints? So these constraints you can figure out basically by doing what Costas showed you. But for higher points, what you will find is that this need to satisfy the following relations. So first of all, here you notice that I only used I less than j, which gives me the degree, give me the freedom to define, to require that ij is symmetric. And also the diagonal ones, I can set them to minus delta I. This is just a choice because they don't show up here, okay? Now with this choice, it's convenient to write down the constraint needs to be satisfied by delta ij, which is if you sum over one index j and with I fixed, you get 0. Now, if you have worked with flat space amplitudes, this should look familiar to you because these are precisely the relations satisfied by the Mandelstam variables. So more precisely, you can think of some imaginary auxiliary momentum in flat space, and you can parameterize delta ij as pi dot pj, where the pi squared is minus delta I. So this is like mi squared. And the sum of pi is 0. So this momentum conservation set on shell with delta I as its squared mass, and it's conserved. And you can see these constraints will be automatically solved. So this gives you some motivation to think of the function m, the transformed correlator, as a sort of amplitude. Okay, now let's look at, so now I will convince you that this is actually a very convenient language by looking at the tree level Witten diagrams we looked at before. So,
sorry.
Yes.
Delta and delta ij there.
Which delta?
The integration variable.
Yeah, I just meant the ones after solving the constraint, Yeah.
So this is so delta ij is made out of the momentum.
No, I mean that's just like you don't need to parameterize it like that because these are the same relations satisfying Mandelstam variables in flat space. This is just easier for you to see, like the connection.
Is it a continuous variable?
Please, the delta ij, yeah, they're continuous. Yes, yeah.
And how is it related to the right-hand side? There is
left-hand side,
the ij index. I mean,
where? Here? Sorry, where is it? ij index?
There is no ij on the left-hand side.
There's no ij because
I
have right.
And the left-hand side contains only
xij.
xij.
Yeah. So here I'm suppressing the S5 variables. So I'm just looking at xij. Yes. So xij on the right-hand side only shows up here. So these delta ij's are sort of the dual variables for xij. Yeah. Okay. Now, why is this good? We can go back to the Witten diagrams we looked at it before. And here, let me consider actually more generally some contact Witten diagram that has 2L contracted derivatives at the part of the vertex. So you can show in many space, this just becomes a degree L polynomial in the Mandelstam variables. And this is precisely what you get in flat space, right? So if you remove the bubble and think about a compact Feynman diagram like this, what you will get is also a degree L polynomial. Now for the exchange diagram, it's going to be similar, but slightly different. So what you get is a sum over simple poles. So, sorry, I should write. So we are looking at an S-channel diagram. So here, this delta ij's for 4-point, I can parameterize using ST and U, right? So it will be sum over poles in U in S, starting at the conformal twist of the exchange operator, plus, in general, infinitely many satellite poles. So there's the leading pole, and then there's satellite poles. And the residuals are polynomials in the other independent Mandelstam variable of degree L. So this is also similar to flat space, and there's also some polynomial terms that you also get in flat space of degree L minus 1. So the main difference is that in flat space, you just get one pole. But here you have infinite many poles. This has to do with the fact that not only we have the conformal primary, but we also have these conformal descendants obtained by acting with derivatives. That's why you have infinite many poles. So in general, the sum over n is infinite. But for our problem, you will find that this sum actually truncates to finite many terms. And this has to do with the thing we observed in the previous lecture. So when your spectrum satisfies certain relations, you can trade your exchange diagram for finite many contact within diagrams.
Is there an argument for why there's no cuts?
Here? Yeah, it's essentially because so here, if you expand in like xij, small xij squared, you get only powers. And after you do a many transform, you get poles. But that's a very good question. So how do you, I mean, in flat space, we get cuts. So what happens is that when you go to flat space, you need to go to the high energy limit. So the poles are going to condense into cuts. Yeah. Now, with this technology, we can compute much more easily these holographic 4-point functions. Not just one by one, actually, we can now compute all of them in one go. So let me outline how this is done. So the strategy is to translate the task of computing correlators to solving an algebraic bootstrap problem in embedding space.
Sorry, can I ask one more question?
Yes, of course.
Say you have a flat space amplitude with a cut.
Mm-hmm.
Is there only one melon amplitude with poles that in the flat space only gives that amplitude?
Oh, there are many.
There are many.
Because if I change delta a little bit, it wouldn't matter because they all, I mean, if you, let's say, by finite amount, it should be divided by like r squared, right? So that goes to 0, the difference goes to 0. Yeah. Okay, so this is strategy. We want to reformulate, we want to translate the problem. And how do we formulate such an algebraic bootstrap problem? We do this by imposing symmetries and consistency conditions. So there are four conditions we can impose. First one, and the most important one, is superconformal symmetry. And easy way to do that is to translate this identity, this result, into Mapping space. So this already has taken into account all the consequences of conformal symmetry. And to go to Mapping space, we basically just do Mapping transform on both sides. So the left-hand side, if you do the, maybe let me use different color. The left-hand side, if you do the Mapping transform, gives you the Mapping amplitude. And for this reduced correlator, we can similarly define something which I'll denote as M tilde. This will be the reduced Mapping amplitude. And what about, I'll measure this kind of later, but what about this term? So this term, you should interpret in Mapping space as 0. This is because, like, if you take, let's say, a monomial and do the Mapping transformation, the Mapping transformation is actually ill-defined. But you should set to 0 because these terms, they actually arises as some sort of 0 times infinity effect, 0 being the amplitude. Infinity comes from the opposed getting pinched at poles, and then you get something finite which corresponds to that. But here we just want to know about the amplitude, so let's just set them to 0 and it's fine. What about this R? So this R, I wrote down, it's some product of cross ratios, which you can show that it is some polynomial of U and V. It's a finite polynomial of U and V. Now, this thing is actually easy to interpret in Mapping space because the Mapping transform I erased, if you specify to 4 point, has the following form. So you basically have only 2 independent Mandelstam variables, f and t. And then the xij part will be something look like this, right? And then you have gamma functions and your m and o, s, and t. Now, if I have some factor here coming from multiplying like a term in this R, what should I do with that? I can get rid of it by doing a shift. S goes to S minus 2m, and t goes to t minus 2n. Then I can bring it back to this form, right? So what this tells you is that the factor you multiply, it becomes a difference operator. And then do this for all the terms in this factor R. So basically, you are promoting this factor to a difference factor R hat. Now, we go back to this this result. What you find is that I have a relation between my full Mapping amplitude and the reduced Mapping amplitude. They're related by some difference operator. A sort of loose analogy with respect to flat space would be, so this would be the full super amplitude. This guy is the delta function of supercharge. And this is sort of the reduced amplitude for supergravity, it's 1 over STU. Okay, so this identity, this difference equation takes into account all the consequences of superconformal symmetry. Now, the second requirement we impose is that we have both symmetry or crossing symmetry because we are dealing with bosons. Basically, it says like you can, interchange your the order of particles, and then you also permute these Mandelstam variables. Your amplitude should be invariant with respect to that. And the third condition, which is also important, is analytic structure of the Mapping amplitude. So what we really are imposing here is that it has only simple poles. M should also only have simple poles, with polynomial residuals. The reason is because we know that the correlator could in principle be computed as a finite sum of these tree-level diagrams. And this is the analytic property of these tree-level diagrams. And then there's the final constraint regarding the high energy behavior at the Mailing amplitude. Asymptotic behavior, which says that the amplitude should only grow linearly, linear growth. So the reason is the high energy limit of Mailing is related to the flat space amplitude. So the intuitive explanation is like when energy is high, you don't see the curvature because curvature, at short distances, it's flat. So, and in flat space, we know the tree level amplitude grows at most linearly. Okay, so all these conditions, when you take them put them together, it is extremely constraining. That means, okay, great. Yes. And then you can try to solve this problem. And so notice, like when I formulate this problem, I haven't specified what K1, K2, K3, K4 are. So you can actually just solve all correlators in one go. And you find that the final answer is surprisingly simple. So basically you have some coefficient depending on I and j. Here you have some monomial or your asymmetry variables. Then you have basically, let's write this more clearly. You have some sort of simultaneous pulse in all three channels. Mu minus um plus 2, so plus 2i. And here, like these ijk's, they need to satisfy some triangular relation, so it's actually some finite sum. So this is the result for all these 4-point functions. And these aijk's, you can solve them by basically by imposing all these conditions. And notice when in getting this result, we haven't computed a single Witten diagram. And if you remember what I mentioned from the previous lecture about the S-matrix bootstrap program of Geoffrey Chu, so his idea was to get the amplitude by imposing a number of conditions such as unitarity, analyticity, and so on. That was very difficult to do and didn't succeed. But here in this simpler setting, it is actually possible just to impose supersymmetry and some basic consistency conditions. I guess I'm out of time, so let me maybe just mention like, okay, I'll mention next time. Okay, any questions?
It's not any questions, so.
This has been all for local operators, right?
Local operators. So far, it's the local operators. Next time, I'm introducing non-local defects. Yes.
The question? So the Milling transform.
Yes.
Is it the only way? Is it the unique way to do this? You mentioned that it's like a Fourier transform.
Yes.
I mean, is this the only way to?
No, I mean, you can also do it in position space. In position space.
Oh, okay.
The thing is like it's the analytic structure is more complicated. You can do this case by case, but here the advantage is that you can do everything in one go because you can sort of export. You can use your intuition from flat space because after the Mailing transform, everything just works like flat space tree level. Yeah.
It looks like all the non-trivial information is in these coefficients AI, JK there. So
That's it. Yeah.
how difficult is it to compute these? Can you compute them like in closed form?
Oh, yeah, this is computed in closed form for all of them. There's a closed form formula, yes. And you can see this looks like, I mean, if you STNU enlarge, there is precisely one of STNU. So like what I said there, yeah.
So if I can speak again.
Okay.
Does exist. We can, yeah, in this situation, there's one of the historic signature of QT in Will the students come here? Yes, students are coming. No, but I don't see them in front of me. Okay, students, please come to the front. For you. I am not starting until I have a couple more.
No, you keep one here. So you're not, you don't want to take the. So that's what we have in.
Thank you. Okay, so welcome back. QFT and Decider Lecture 2. Let me remind you a little bit about what we discussed last time. So last time, we introduced Decider. As the simplest cosmology. So we wrote down an equation for Decider. We wrote it like this in d dimensions. The equation of constraint in a d plus one dimensional spacetime equaling to a certain length scale. And you can clearly see that this very much mimics the equation for a sphere. The only difference between this and the equation for a sphere is that there's a minus. The equation of constraint in Minkowski space rather than Euclidean space. Sometimes people call this metric or this spacetime the pseudosphere. If you ever see the word pseudosphere, now you know that they mean Decider. So we can write this as follows. Write it as say AV equals L squared, where this is the Minkowski metric. D plus one dimensions. So the Decider space is an equation of constraint in a d plus one dimensional spacetime. So this describes a d-dimensional space. D plus one coordinates, one constraint kills one coordinate. We have a d-dimensional spacetime, and we drew it as follows. This is x0. Can't draw as many dimensions as I want, so I'm going to have to just do two-dimensional Decider, and we drew it like this. 0. And we explained how the space-time describes an inflating cosmology because as time goes forward, the spatial slices grow. Last time we also talked about the fact that this was a maximally symmetric spacetime. We said is maximally symmetric, which means that it has the same number of isometries, of symmetries, as d-dimensional flat space, which means that it has d times d plus 1 over 2 symmetries. So these symmetries were boosts and rotations. And so today we're going to talk mainly about these symmetries and how these symmetries constrain particle field. How we use these symmetries to describe the basic building blocks of QFT in de Sitter space. And I'm going to do it in a very gentle way, hopefully, by reminding you of, as we go along, of how it works in flat space and then working by analogy how it works in de Sitter. Okay. Are there any questions so far? Okay, so already filled out the board, so I need to erase. Okay. So what are these symmetries? So remember, we talked about these symmetries were the boosts and rotations. So there were, see what, if I got the counting right. Yeah, I think it's, well, there are D boosts and D times D plus 1 over 2 minus D rotation. Okay, so how do I write down these isometries? So remember, I'm going to write up the space-time up here and hopefully never erase it. I'm going to write this as. Okay, so how do we write the isometries of the spacetime? Usually what we want to do is we want to define them via infinitesimal operators that generate symmetry, right? So for example, we want to find the various operators that rotate or boost the slices. And using these coordinates, using these, what these are called embedding coordinates, these are, so we have to solve the constraint to get coordinates on de Sitter, just like we did last time. And in terms of these embedding coordinates, it's very simple to write down the isometries of de Sitter. So let me write those down for you. So the infinitesimal generators.
One question.
Yeah.
How about discrete symmetries? Like triangle version symmetry?
So
maybe parity.
So those are also there. So I'm only going to talk about the continuous. We can talk about the discrete symmetries if you want later, but they're not going to be important. So the infinitesimal generators are very simple to write down. I'm going to define LAB. I'm going to write it just like this. Notice that these A and B are down, and these A and B are up in the derivative. That's on purpose, so be careful. Otherwise, you'll get the signs wrong. So these are differential operators, and if you act on functions on de Sitter space, these will generate the rotations. What does it mean that they generate the rotations and the boosts? Well, it means that they have a commutator algebra. So if I write commutator between any of these two operators, then I get the following. So has anyone seen this algebra before? You guys recognize it? Is this new? So shake your head if you've never seen it. Say it like this. You've never seen it. Have you guys seen it? Never. You've never seen it.
Is it not like a metric? No, not really.
You guys over there.
The algebra.
It is definitely a Lie algebra. So this is a commutator. So yeah, in general, when we have infinitesimal generators of a symmetry, that means that, okay, if you have a little quick group theory discussion, if you have a group symmetry, that means that the group acts like by multiplication. And usually when we think about small generators, small translations, then we can write the group, so something like GAB, we can write it as e to the I LAB, where LAB is something called a generator. And the group multiplication rule for the group turns into a commutator relation for the algebra. So when I write this down, I really mean that this encodes the full group action here, but I'm writing in terms of the infinitesimal generators. So these generate small amounts of rotation. I'm not supposed to think of these as generating big ones. Now that that's been said, it's okay if you've never seen this. Very good. Yeah, that's right. This is exactly the Lorentz algebra. So this is these are the commutation relations for the Lorentz algebra. So this is the same algebra that you find in flat space. But in flat space, so this is the Lorentz algebra in one higher dimension of flat space. And that shouldn't be surprising because we started with an equation of constraint in d+1 dimensions. And these are just the generators of the Lorentz algebra in those d+1 dimensions. So, so the symmetries of de Sitter are just inherited from the Lorentz group in the one higher dimension that we defined. And the only part that we don't get to keep are the translations. No time translations and no space translations. So this is the Lorentz algebra in one higher dimensions, and sometimes that is referred to as SO1, comma E. For example, four-dimensional Lorentz algebra is SO1, 3. For de Sitter in 4 dimensions, it's SO1, 4. Okay, so well, I'll interchange the words Lorentz group and Lorentz algebra. So this is D+1 dimensions.
All right.
Yes.
So 1 comma d+1.
No.
Your notation above.
You have d+2 total.
Finished by d+2.
Ah, sorry. Sorry. Thank you. This should be an equation of constraint in d+1 dimensions. I accidentally wrote d+1. Thank you for catching that. This is SO1. Now you agree with us. Thank you. Sorry. The same as last time. So I'm pretty sure last time I wrote D here, not d+1. Check your notes. Okay, so I'm gonna now tell you, I'm gonna remind you something. So everybody here has taken quantum field theory before, or at least seen something about quantum field theory. Students, help me out. I can't know if you don't speak.
Yes.
Thank you. Okay, so in quantum field theory, we label states using representation theory. Our symmetry algorithm. So today we're going to talk about the allowed states of this symmetry algebra. We're going to work using examples. The simplest example of a quantum field theory is a scalar field theory. Okay. Let me write down the action. The action for a scalar field theory, any manifold, is minus 1/2 integral to x square root of minus g mu nu d mu. And let me integrate this by parts. The same thing as minus 1/2 e to the dx g minus, and I'm going to pull out a phi here, minus okay. So this is just a scalar field theory. And if I vary my action with respect to phi, I get an equation of motion. Equation of motion is just this differential. Okay. So let me tell you how that works in flat space. So in flat space, that means g mu nu equal to eta mu nu minus 1, Say we're in 4 dimensions, doesn't matter. Then this equation right here is dt squared minus the x squared plus m squared. Equals 0. Right? Is that correct? You guys agree?
Wait, minus. You this minus plus plus.
Yeah, minus, there's a minus here. Okay.
Yeah.
Okay. And often what you see is people go into write things in momentum space. They Fourier transform this equation, and they write this like this: d mu minus m squared phi. So this is the same as the equation d mu on phi is equal to. Now I'm going to interpret this equation in. Well, it depends on if you define it with an I or not. I want this, okay? So what people call this is they call this the Casimir operator. This is a quadratic differential operator that commutes with all the elements of the symmetry algebra of Minkowski space, or the quadratic Casimir. And the quadratic Casimir operator as an eigenvalue equation is a statement of that you are studying the representations of the algebra, and you're labeling them using the eigenvalue of this operator. So you may remember that from studying, for example, angular momentum in quantum mechanics. You study the angular momentum operator, you have an operator you call L squared, or maybe curly L squared. And its eigenvalues, you label them as L. This was a quadratic operator. It had eigenvalues, and this operator commuted with Lx, Ly, and Lc, right? So here, p squared, same thing, it's a quadratic operator, commutes with all the generators of Lorentz and Poincaré, and it has an eigenvalue, m squared. But what we say is actually the rest mass, so in flat space, the rest mass is actually Lorentz label or Poincaré label. And as far as physics in flat space is concerned, the only thing that we care about is the particle massive or is it massless? Of course, we're talking about scalars. We have higher, when you have spins, then we have other, but this is just for a spinless particle. So the only special cases are massive and massless. And the mass is the label of the representation of the element. Okay? So in a similar way, we're going to study the representations of this equation over here when it comes to de Sitter. Okay? And it gets a little bit more complicated. Okay? Is it clear? Let's redo the answers. So let's repeat the exercise in de Sitter. So in de Sitter, the equation, we still have the same thing. Now we're working with this equation. Where this is the Laplacian on de Sitter. And if I write it in terms of the LAB before, this is just I think we're fine. Okay. So just as before, I have quadratic operator. And it commutes with all elements of the algebra, just like the Klein-Borden equation in flat space. Okay. And now the eigenvalue equation. We can write it like this. Okay. So this is the quadratic Casimir of SO1D. The difference between flat space and de Sitter is that the other one was the quadratic Casimir of Poincaré. This one is the quadratic Casimir. And the quadratic Casimir of SL1D, as you can see, this is very much so. If I do an analytic continuation, this should have a very similar structure to the group theory of SOD plus 1. Just one analytic continuation from SOD plus 1. Sorry, SO. And remember, the labels for so the labels for a sphere were like L plus 1, the quadratic Casimir for and the angular momentum operator in quantum mechanics was like L plus 1. And so here, the quadratic Casimir for this guy is SO1D. We often label it using this quantity we call delta times delta minus. And so now this delta labels. So we can solve this equation. This part of the blackboard has done its duty, so I can erase it. So let's solve this equation. There are two solutions. And you will immediately notice something. You'll notice that for m squared L squared smaller than d minus 1 over 2, these quantities are real. But for m squared L squared greater than d minus 1 over 2, these quantities are complex. Okay? Complex solutions. So unlike in flat space, where there was just a difference between massless and massive, in de Sitter, we have a scale determined by the curvature scale of de Sitter, this length scale L squared. And there is a notion of a heavy particle and a light particle. So this is the notion of heavy. This is the notion of light. And their behavior is quite different. Okay. And that's just for scalar fields. Okay, so
just to be clear, you are just defining your LAB that thing as delta bracket delta this thing, and then you are solving this in like higher dimensional sphere L equal to L minus this thing. Similarly, you are just instead of L you are defining delta, right?
Correct. Okay. Correct. It just turns out just like how L is a useful label for the sphere, because for example your irreducible, so on the sphere what happened is that your irreducible representations go from minus L to L. Here this delta is useful in the same way. So each delta labels an irreducible representation. There's going to be a certain number of states in each representation. That number is labeled by some other quantum numbers, just like n. Any other questions? How am I doing all the time? 35. Okay. So
So you have delta times delta minus d minus 1.
Yeah.
What is the reason for the d minus 1?
What is the reason for it?
How would we motivate the presence of the D-1?
Well, it's very similar to what happens for a d-dimensional sphere. So L times L plus 1 is for the S2. But if you have an S3, it's L times L plus 2. S4, L times L plus 3. So it's the same. It's just a useful label because if you define it this way, then all the representation theory doesn't depend heavily on the equations of the representation theory don't depend as heavily on dimension. Just a useful way of breaking up this like that.
L squared, should it be less than or equal to for the real solutions?
So for real, it's less than or equal to complex. Any other questions? So now I'm just going to tell you, because if I spend too much time explaining this, it'll be a bit boring, especially because this is the result of what mathematicians have studied, not what physicists have studied. So I'm just going to tell you, actually, all the okay. So let me summarize quickly. Delta labels what are called the unitary, irreducible representations of SO1. Okay, and I was mentioning that there's a notion of light and heavy, but actually mathematicians worked pretty hard, and they discovered that light and heavy doesn't exhaust the unitary irreducible representations of de Sitter. So let me give you an example of that. I'll give you the simplest example. I'll give it to you in D equals 2, two-dimensional de Sitter. Okay. So what happens in D equals 2? Okay, so in D equals 2, we have what the following option: delta is equal to 1/2 1 plus I times some imaginary number. So that's the case m squared L squared greater than a quarter. And this, so I'm going to give you the name of the representation. This thing is called principal series. And its behavior, so the mathematics of this representation, I'm not going to talk very much about, but it's a distinct unitary irreducible representation. And so I'm introducing the name just in case you want to read the literature of it. When people say principal series, you just have to think, that means a heavy particle in de Sitter. Okay. Then the other case that I mentioned earlier, which is these are called complementary series states. And they label light fields, or they describe light fields. So now if you read in the literature and you see somebody say complementary series, that means light field. So for example, the scalar fluctuations in the CMB were of this type, complementary series, light fields. And then, so you might think that's it. That's all I have. However, there are a set of distinct states with delta equals 1, 2, 3, 4, 1. These people are called series states. And I want you to guess what kind of mass squared that corresponds. You have it in your notes. Maybe if you stare at the solution of the equation that I wrote down. Plug in d equals 2. Try to figure out what would give delta equals to 1.
Arbitrary real?
Yeah. This is just write this. Any guesses? So we talked about light particles, we talked about heavy particles. What could give delta is equal to an integer? I'll take any guess. M squared, L squared, less than 0. Yes. So M squared, L squared, if it takes special values like this, where t is equal to 0, 2, right? This one is t equals 0. Then you can get a unitary irreducible representation. So that's very strange. That's very strange. So the mathematicians discovered something. They discovered that there exists unitary irreducible representations labeled by tachyonic masses, so m squared less than 0. But then when I write down the action for such a particle, well, if I try to do the path integral for it, it has a negative mass squared. Even the Euclidean path integral doesn't make any sense. It's very strange. So this is the first place where de Sitter physics is very different from flat space. In flat space, every single unitary irreducible representation has a corresponding free action. Okay? Write down a free action in flat space. So for example, of a massive particle or a massless particle, and I can work to quantize it. In de Sitter, the mathematicians have labeled the unitary irreducible representations. For the heavy particles, I can write one down, no problem. It's heavy mass. For the light particles, I can write one down, light mass. I can try to write this down, but I actually don't know how to quantize it. So it's a little bit complicated to work. So this mass squared looks a little bit peculiar. Let's study it a little bit further. Okay. I just want to highlight before we go forward. This has local free Lagrangian description. And we'll see why now in the case of d equals 2. I'll explain what goes wrong d equals 2. Okay. Any questions?
I have one question. Are people still working on this tachyonic states? I mean, is this a research area or?
Yeah. I'm very interested in them. I think that they're very bizarre. Okay, so a little bit more motivation before I jump into why people might consider them. So you might think, okay, so have any of you heard of these representation in these continuous spin representations in flat space? Has anybody heard of them? So there are also weird representations in flat space that that exist. You can classify them and you might write them down. And people thought hard about them for particle physics in flat space, but it turns out that if you ignore them, you could never produce them in like starting from a theory that doesn't have. So it's safe to ignore. What happens in de Sitter, you might think the same thing. Okay, let's say I have a theory that doesn't have tachyons, and I just don't ever input them by hand. And I just want to have a self-consistent theory that doesn't include. Well, the mathematicians have also studied tensor products. So for example, if I take a delta labeled by mu and I tensor product with a delta labeled by nu, then you better hope that you get either heavy and light stuff. But it turns out that if you study this, mathematicians have studied this, you get stuff labeled by this discrete label, tensor summed with delta labeled by nu prime. So you get a bunch of stuff that's heavy plus tachyon. If you take two massive particles and you bring them together, actually you need the tachyon states in their the resolution of the identity, which is very bizarre from a physics perspective. So that's why I think they're worth studying. So even if you want to ignore them just out of principle, mathematicians have told you that you can't. You're not supposed to. Okay, so let's go back. So I said that the discrete series had delta equals 0, 1, 2, so on, m squared, l squared equals, let me write it like this, delta is equal to 1 plus t, and m squared is t plus 1 for t equals 0, 1. So the first discrete series particle is actually a massless scalar. So let's try to understand what goes wrong, why you can't write down action, local action for a massless. So what goes wrong with this? So the simplest argument I can give you for what goes wrong with a massless particle is the following. So say that I want to study a correlation function. I'll explain more what this notation means later for a massless particle. Okay, I'm going to call this the Green's function G. Okay, so because it's formed out of a product of correlation of fields, and the fields themselves obey the equation of motion, then the equation of motion log squared g is equal to 0 should be satisfied. Actually, it should be satisfied everywhere except for when x goes to y. So we usually write this as delta xy. That's the equation of motion for a correlation. Okay. Now, that's what we might imagine for a massless particle on the sitter. But often, when we want to study these correlation functions, it's much easier to study the problem in Euclidean. We want to study this problem in Euclidean. So let's analytically continue ds2 to ds2. So now we're working with quantum field theory on a sphere, right? So ds2 looks like this. We continue it to the sphere. Now, I'm just analytically continuing this equation in motion. This equation is now the Laplacian on the sphere. Okay. Maybe there shouldn't be any problem. Let's see if this admits a reasonable solution. Can anybody see a reason why this might not admit a reasonable solution on the sphere? Any guesses? I'll give you a very quick reason why it shouldn't admit a reasonable solution on the sphere. Let's integrate it over the entire sphere. Let me integrate this equation over the S2. Okay, so the right-hand side equals 1. That's very clear. What about the left-hand side? The integral over total derivative on a closed manifold? 0. 0, can it equal 1? No. But this equation doesn't make any sense. Okay. That's just a statement that there should be no free, a free local action for a scalar field with no mass on the S2 doesn't make sense. And by analytic continuation, it also doesn't make sense on DS2.
It's not directly see it on DS2 because it's not the compactness of S2 is giving rise to it's probably possible to do something like that.
I can give you an argument, but it's not as quick as the one I just gave. Let me give you the argument. Sorry, how much time do I have? 15 minutes. Okay, so I'll give you a quick argument.
I may cancel my first opportunities over.
No, it's okay. I'll give you a quick argument for all of them, which will continue. Okay. So let's study the path integral. Let's study the path integral for this field Z on the S2. Right. So we're going to take the mass squared to be this. So this is equal to the path integral over phi e to the minus the Euclidean action. The Euclidean action is the integral over the S2 square root of g phi minus ox squared minus t times t plus 1. Okay. And now what we do, because this is on the S2, we can expand phi into a sum over the spherical harmonics on the S2. Right? We know that the Laplacian, when it hits YLM, gives LL plus 1. Right? So if I write this out, the path integral then becomes an integral over these coefficients. And it's a bunch of Gaussian integrals. So I have dCLM e to the minus L plus 1 minus t plus 1 CLM squared. And these are Gaussian integrals, right? And we immediately see that you can do these Gaussian integrals for all the CLMs except for L equals t. For L equals t, there's no Gaussian suppression. The L equals t family is a problem, right? And so I need to figure out a way to deal with the L equals to t family.
What's the range of L?
So L is from L equals 0 to infinity. So these are just the spherical harmonics on the sphere.
The flip Gaussian is okay to use somehow. If the coefficient is coefficient in the parentheses.
Yeah. So one way to deal with it is either you remove all the L's below T, or you analytically continue a finite number of these C's. But the
zero is dangerous.
Zero is dangerous because it's absolutely flat. There's no analytic continuation that you can do to make this path invulnerable. So you have to figure out, so at the very least, you have to delete one family. And there's no local way to delete one family. There's no local thing that you can do to this free action that will just delete one set of modes this way. And so already there's some kind of potential non-locality going on in de Sitter, and this is an unsolved problem. These are unitary, irreducible representations. They're important for de Sitter particle physics. We don't know how to represent them using free Lagrangians, free local Lagrangians. So already we have one place where the quantum field theory on de Sitter is directly different from quantum field theory in flat space. And you might think, oh, this is just a problem in d equals 2. No. It also arises in d equals 4. There's an analogous version of this problem in d equals 4. Okay. So we need to understand this. One day maybe we will. I'm gonna move on. I have what, 10 minutes left? Yeah. Okay. So now I'm going to tell you, I'm going to finish by telling you one more weird thing about de Sitter that we take for granted. Not that we take for granted, but needs to be remembered. And so let me just discuss that now. Let's see. Okay, so let's go back to so now let's go back to d dimensions. And say we want to quantize this scalar field. First thing that we do in flat space is we promote these scalar fields to operators, and we define a vacuum, right? So what we do in flat space is so we take phi to be an operator, and we impose something called canonical commutation. That means at fixed time, but separated points, these fields commute. But not with pi is defined by dl d by dt. Okay. So the way that we usually ensure that these canonical commutation relations are obeyed is we take phi and we expand it in modes. I'm going to write it as a discrete sum, but it's represented as an integral. There are annihilation operators, and some mode function depends on coordinates plus a dagger. And these canonical commutation relations are the same as writing AP E dagger, AP prime dagger 0, but dagger. And then this state over here, O, is defined as the vacuum annihilated by all the AP. So what is the statement that AP annihilates the vacuum? It's the statement that all translations are a symmetry of the vacuum. So this vacuum obeys that it is invariant under all of the symmetries. And what does that ensure? That ensures that if I define this correlation function, g of xy, then g of xy has to be a function of something called the invariant distance, sigma of xy. Sigma of xy has to be something that's invariant under the symmetries of flat space. And that sigma of xy in flat space still, that sigma of xy is just x minus y mu, and of mu nu, x minus y mu. Okay, and this thing that's called O in flat space is unique. Okay, so now let's do the same thing in de Sitter. Actually, let me say one more thing. How do we know that it's unique? Well, so this thing solves a differential equation, and there are two solutions to the differential equation. It's a second order differential equation. And one of the solutions we can always throw away because it grows at long distances. And we know that these correlation functions can't grow. So that's how we know that the vacuum is unique. Only be one of the solutions allowed. Okay. So now what is let's solve the same thing in de Sitter.
With a dagger.
Thank you. So flat space vacuums. So now let's study the problem in de Sitter. So in de Sitter, you would do the same thing. You define g of xy is g of sigma of xy. The de Sitter invariant distance, since you want this thing to be de Sitter invariant. And now that sigma of xy in de Sitter, you can guess it. It's just is x minus y a theta a b x minus y b, and we'll divide it by 2 elsewhere. And because x and y are coordinates on this hyperboloid, this is the same as 1 minus xa b yb L squared. This quantity I'm going to call P. It's the dot product between x and y. The reason you get a 1 here is because x dot x is equal to L squared, and y dot y is equal to L squared. Okay? Okay. And now this quantity, we impose the Klein-Gordon equation, and this g of sigma, there are two solutions. I'm going to write it as g of p. So there are two solutions. Delta plus is the same delta plus as before. Delta minus is the same delta minus as before. P over 2, 1 plus p 2, and b times 2f1 plus minus 2. Okay. And now we can try and do the same thing as in flat space. Maybe we want to throw one of these out because they grow. All or have some problems as we go. And these 2F1s, students tell me, have you guys heard of these? They're called hypergeometric functions. No? So if you want, maybe look up the Wikipedia for hypergeometric functions. Okay, so what happens? Can we throw out the growing solution like we can in flat space? Well, there must be a reason why I'm bringing this up. Okay, what's the guess? No, we can't. So why can't we? Well, let me tell you why we can't. So what happens is that so this one, so these 2F1s, I'm just going to tell you, this one is singular at P equals to 1. So P equals to 1, and C is X equals to Y. Right? P equals to 1, singularity at P equals to 1, that's just the coincident point singularity. That's the one that you would expect. And this one is singular at P equals to minus 1. So P equals to minus 1 is X equals to minus Y. This is a configuration with P equals minus 1. And in flat space, this kind of singularity is completely unacceptable. It means correlations across very large distances. But in de Sitter, no experimentalist could ever observe this violation. Because as I mentioned in the last class, in de Sitter, an observer sitting somewhere in this expanding universe has a horizon. There's a region beyond which they can't see. And this P equals to minus 1 point is beyond that horizon. So there's no reason to throw out the second solution. There's no physical basis for why you would throw out the second solution. So in de Sitter, the vacuum is not unique. Main difference with phosphorus. So we don't have any reasonable way to argue that this guy shouldn't be included. But what people often do is they argue from the Euclidean picture. So in Euclidean, de Sitter is a sphere. And on the sphere, these P equals to minus 1 configurations are again configurations where if you take two fields to be antipodally separated, there's a singularity, there's a high correlation. And so we argue based off of the Euclidean picture that the preferred state, I'm going to put a may better defined in Euclidean. But this is just speculation. So often what people do in the literature is that they just work, they do still ignore this guy. And they do so by arguing that the physics should be local in the Euclidean continuation. But of course, from a Lorentzian perspective, that you'd have to come up with another argument. And I don't have a good argument to give you because nobody does. Take another minute. So one last thing I want to tell you, and this connects to Kostis' talk, is that if you look at this correlation function, tells you one more thing about de Sitter, and that's the thing that I'm going to end on. And it's that quantum fields in de Sitter are thermal. They're in a thermally populated state. And the simplest way to see that is just the statement that Kostis made earlier, is that in the Euclidean, this correlation function is periodic in Euclidean time. And any correlation function that is periodic in Euclidean time, we associate with a thermal state. So, T in de Sitter is 1 over 2 pi L. And this is related to the fact that this spacetime has a horizon. You may have heard that black holes have a temperature, it's the Hawking temperature, because there is a horizon. And this spacetime I mentioned earlier also has a horizon. It comes from the expansion of the spacetime. And it's the same effect. The temperature of this spacetime is the same temperature as the thing that gives rise to the black hole temperature. And it has to do with the fact that the Euclidean picture is compact and there's a symmetry going around the Euclidean circle. So there's a lot that is weird about de Sitter. Tachyons are allowed, but they're not local. They have to be there for some to explain things in the particle theory on this background. The background in the ground state is thermal, which is also weird. And the ground state is not unique. We don't have a Lorentzian reason to argue for its uniqueness. So there's plenty to understand, just very basics, very much basic stuff about de Sitter. You see, everything that I presented today has to do with free scalar field theory. I haven't even turned on interactions yet. So you can see that there's still a lot to discover about this stuff.
Which that a lot. There's my favorite field.
Cosmological horizon. Yeah, that's the one.
There are other questions. Let's find the beginning.
Yeah, we'll see tomorrow.